Listen closely. That low, resonant hum vibrating through the silence of space is not science fiction. It is the actual sound of a black hole, a deep bass note echoing across 1,000 light years, a ghostly whisper from the ultimate edge of reality. It is a sound that should not exist in the vacuum of space, and yet it does, a perfect metaphor for the objects themselves, these cosmic paradoxes that defy every rule we think we know. They are the universe's greatest magic trick, and the more we learn, the more impossible they seem. Today, we are going to journey into the heart of that impossibility, to explore the 30 most profound unsolved mysteries surrounding black holes and the terrifying singularities at their cores. These are not just academic curiosities, they are the fundamental puzzles that challenge the very foundations of physics, questions so deep that answering them might just rewrite our understanding of existence itself. Think of the most mind-bending science fiction movie you have ever seen, one where gravity twists time, where space is a fabric that can be torn, and where a point of infinite density hides behind an event horizon from which nothing, not even light, can ever return. Now imagine that movie is not fiction. It is the documented reality of our cosmos. Black holes are that reality. They are the universe's ultimate paradox, simultaneously the simplest objects described only by their mass, spin, and charge, and the most complex, harboring secrets about the nature of space, time, and information that have baffled the greatest scientific minds for decades. From the moment their existence was more than just a strange solution to Einstein's equations, they have captivated us, representing both an end and a beginning, a destructive force and a potential key to unlocking the laws of quantum gravity. This video is our expedition into that captivating unknown. We have compiled 30 of the most perplexing, awe-inspiring questions that these cosmic monsters pose. We will start from the surface, from the event horizon that acts as a point of no return, and venture inward toward the singularity, a place where the laws of physics as we know them simply break down and cease to exist. Along the way, we will grapple with concepts that sound like pure fantasy: wormholes, white holes, firewalls, and the holographic principle. We will question what truly happens to matter that falls in, whether information is truly lost forever, and if these bizarre objects could be gateways to other universes or even the source of our own. So prepare to have your perception of reality stretched and reshaped. The journey ahead is strange, counterintuitive, and utterly fascinating. Let us begin with the very first mystery, the nature of the event horizon itself. Our journey inward begins not at the singularity, but at the very boundary of impossibility, a surface known as the event horizon. This is the black hole's point of no return, an invisible spherical shell surrounding the abyss. Once anything, a star, a spacecraft, or even a single particle of light crosses this threshold, its fate is sealed. There is no force in the universe powerful enough to pull it back out. The gravitational grip is absolute. Think of it as a cosmic waterfall. You can paddle calmly in the river upstream, but once you go over the edge, the current pulls you down irrevocably. The event horizon is that edge, not a solid wall, but a one-way door in the fabric of spacetime itself. But here is where our first great mystery arises, a puzzle so profound that it has sparked a 50-year war between the two pillars of modern physics: general relativity and quantum mechanics. It is called the black hole information paradox, and it was first uncovered by Stephen Hawking. To understand it, we must first shatter a common misconception. We often say that nothing escapes a black hole, but that is not entirely true. Hawking made the stunning discovery that black holes are not completely black. Due to weird quantum effects happening right at the event horizon, they slowly leak radiation. This Hawking radiation is a faint whisper of energy that, over unimaginable eons, causes the black hole to evaporate, shrinking until it potentially vanishes entirely. Now, this creates a catastrophic problem for physics. According to the bedrock principle of quantum mechanics, information can never be truly destroyed. Information, in this sense, is the unique identity of every particle that falls in, its mass, its spin, its quantum state. If you burn a book, the information seems lost in the smoke and ash, but in principle, if you could collect every single particle and trace its path, you could reconstruct the book perfectly. The information is scrambled, but it is not gone. However, Hawking's calculations suggested that Hawking radiation is completely random, purely thermal. It carries no information whatsoever about what fell into the black hole. So, when the black hole finally evaporates, all that information about the stars, gas, and anything else it consumed is seemingly erased from the universe forever. It is as if you burned that book and the very laws of physics prevented you from ever reading its ashes. This idea of information loss was so unsettling that many physicists, including Hawking's colleague Leonard Susskind, fought against it. If information can be lost, then the entire predictable cause and effect foundation of our universe crumbles. The debate became so heated it was famously settled with a bet, with Hawking initially conceding that information must somehow be preserved. But how, if it does not come out in the radiation, where does it go? This is the heart of the paradox. Several bizarre solutions have been proposed. One is the idea of a firewall. This theory suggests that the event horizon is not a smooth, empty space as Einstein predicted, but a blazing wall of high-energy particles. Anything hitting it would be instantly incinerated before it could even cross the threshold. The information of the object would be encoded on the firewall and then slowly released as Hawking radiation. While this saves the information, it violates Einstein's principle of equivalence, which states that freely falling observers should notice nothing special as they cross the horizon. You would not peacefully fall in, you would hit a cosmic brick wall. Another, even more mind-bending solution is the holographic principle. This proposes that all the information about what is inside a three-dimensional black hole is actually encoded on its two-dimensional event horizon, like a cosmic fingerprint smeared across the surface. The three-dimensional interior is just a projection, an illusion. Much like a hologram on a credit card appears three-dimensional, but all its information is stored on a flat, two-dimensional surface. In this view, when matter falls in, its information is not lost, it is painted onto the horizon. The Hawking radiation then slowly reads this information off the surface and carries it away as the black hole evaporates. This means our universe itself might be a holographic projection, a staggering idea that redefines the nature of reality. Yet, each solution comes with its own profound troubles. Firewalls violate general relativity, while the holographic principle forces us to question the very nature of dimensionality and existence. The information paradox remains one of the most active and contentious areas of theoretical physics, a stark reminder that at the edge of a black hole, our understanding of the universe reaches its own horizon. But if the event horizon presents a paradox, the true heart of the mystery lies deeper within, at the very center of the black hole itself. This brings us to our second and perhaps most profound enigma, the nature of the singularity. According to the equations of general relativity, when a massive star collapses under its own weight, all its matter is crushed into an infinitely small point. This is the singularity, a place of infinite density where the fabric of spacetime curves to an infinite degree and simply ceases to exist as we understand it. It is a mathematical concept that physics struggles to grapple with, a point where every known law, from gravity to quantum mechanics, breaks down completely. Imagine taking the entire mass of a star, or even many stars, and compressing it into a volume of zero size. The very idea is nonsensical, a glaring sign that our current theories are incomplete. The conflict arises from the fundamental disagreement between our two most successful descriptions of the universe: general relativity, Einstein's magnificent theory of gravity and the large-scale structure of the cosmos perfectly predicts that singularities must form inside black holes. It paints a picture of smooth, geometric spacetime that warps and curves until it inevitably tears. Quantum mechanics, on the other hand, governs the bizarre world of the incredibly small. It is a theory built on probabilities and uncertainties, and it has a deep-seated aversion to infinities. In the quantum realm, nature seems to find a way to smooth things over to prevent such nonsensical extremes. For decades, physicists have searched for a way to unite these two theories into a single, coherent framework known as quantum gravity. The singularity is the ultimate testing ground for this quest. Understanding what truly happens at the center of a black hole isn't just about solving one cosmic puzzle. It is the key that could unlock a unified theory of everything. So, if infinities are impossible, what could possibly replace the singularity? One compelling idea comes from loop quantum gravity, a theoretical approach that proposes spacetime itself is not smooth and continuous, but is instead woven from tiny, finite loops, a fabric of discrete threads. In this view, the immense gravity at a black hole's core doesn't create an infinite point, but instead reaches a maximum possible density. The collapsing matter would hit a quantum wall, a sort of ultimate pressure that prevents further collapse. The result might not be a singularity, but a region of extreme yet finite density, a concept sometimes poetically called quantum fuzz. This fuzzball would be a tangled knot of spacetime fabric itself, containing all the black hole's mass without the problematic infinities. Another fascinating possibility is that the collapse doesn't stop at all, but rather continues into something else entirely. Some theories suggest the singularity could act as a bridge, a wormhole connecting our black hole to another point in spacetime, or even to another universe. In this scenario, the matter falling in isn't destroyed at a point of infinite density. It's funneled through a cosmic tunnel and ejected elsewhere, perhaps as a white hole in a different cosmos. While this sounds like pure science fiction, it emerges as a valid, though highly speculative, solution within the equations of general relativity when quantum effects are considered. Ultimately, the true nature of the singularity remains the greatest unknown. It is a place that is, by its very definition, hidden from us forever behind the event horizon. We cannot observe it directly, and our mathematics hits a wall. Any theory of quantum gravity that hopes to be successful must provide a physically plausible description of this central engine. Does matter get crushed into a new, exotic form of existence? Does it pass through a gateway to another reality? Or does it simply cease to be, taking its secrets with it? The singularity is the ultimate frontier, a challenge thrown down by the universe, daring us to look into the infinite and find a new set of laws. Yet if the singularity is a problem of infinities, the event horizon presents a mystery of perception. We've called it a one-way door, a boundary, but what is it truly made of? Is the event horizon a tangible, physical surface you could touch, or is it merely a mathematical line in the sand, a location in space defined only by gravity's irresistible pull? This is not a trivial question, and the answer forces us to confront one of the strangest predictions of Einstein's theory. According to pure general relativity, the horizon is absolutely not a physical surface. An astronaut falling into a stellar mass black hole would notice nothing special as they crossed it. No sudden jolt, no tearing sensation, just the serene, albeit doomed, continuation of their fall inward. The horizon is a place of no return, but it is not a place of drama for the one falling. To make sense of this ethereal boundary, physicists developed a powerful, if fictional, tool known as the membrane paradigm. This approach treats the event horizon as if it were a physical, two-dimensional membrane with astonishing properties. Imagine it as an incredibly viscous, superheated sheet of spacetime fabric. From the perspective of someone outside the black hole, this membrane appears to have temperature, electrical resistance, and even viscosity, much like a stretchy, elastic skin. When matter approaches, the membrane seems to slow it down, stretch it out in a process called spaghettification, and absorb it, releasing energy in the form of Hawking radiation. This paradigm is incredibly useful for doing complex calculations about how black holes interact with their environment, allowing us to model them without immediately grappling with the confusing interior. It is a brilliant mathematical fiction, a convenient lie that produces correct answers, but it raises a deep philosophical question. If something behaves as if it is real for all external observations, in what sense can we say it is not real? This duality lies at the heart of the debate about what a falling observer truly experiences. The peaceful passage predicted by Einstein clashes with the violent drama suggested by quantum mechanics and the information paradox. If information is not lost, and if the horizon must somehow encode the history of everything that has fallen in, does that process leave a mark? Could there be a detectable structure there after all? Intriguingly, recent observations of gravitational waves, the ripples in spacetime from colliding black holes, may hold a clue. Scientists have begun searching for faint echoes in the signal following the main collision. The Standard Model predicts that after two black holes merge, the new, larger black hole will settle down quickly, ringing like a bell but with a clean, dampened signal. These potential echoes, however, could be the signature of something entirely unexpected, a physical structure at or just outside the event horizon. It is as if the gravitational waves are bouncing off a surface, a wall, before escaping into the universe. If confirmed, such echoes would be revolutionary. They would directly challenge the pure Einsteinian view of a perfectly smooth, empty horizon. Instead, they might point toward something like the firewall or another quantum gravitational structure that modifies the immediate vicinity of the black hole. Each echo would be a whisper from the edge of reality, hinting that the event horizon is not just a mathematical abstraction but a region with its own unique physics. The hunt for these echoes is now a frontier in astronomy, a meticulous sifting of the most powerful events in the cosmos for a trace of something that, according to our simplest theories, should not be there. The true nature of the event horizon, therefore, remains suspended between theory and observation, a ghostly borderland that may yet hold the key to reconciling the vast scales of gravity with the tiny realm of the quantum. But if the event horizon is a one-way street into darkness, what if there exists a cosmic exit ramp? This leads us to the fourth great mystery, a concept that pushes the boundaries of theoretical physics into the realm of the truly fantastic, white holes and wormholes. These are not the inventions of science fiction writers, but rather legitimate, if highly speculative, solutions to the very same equations of general relativity that predict black holes. They represent the other side of the gravitational coin, hypothetical objects that are every bit as strange as their dark cousins. Let's start with white holes. If a black hole is a region of space from which nothing can escape, a white hole is its exact theoretical opposite, a region of space into which nothing can enter. It is a cosmic gusher, violently spewing out matter and energy into the universe while forbidding anything from ever falling back in. Think of a black hole as a drain in the cosmic bathtub, pulling everything down. A white hole would be the faucet, pushing everything out with unstoppable force. The mathematics of general relativity is beautifully symmetric, and it allows for this solution just as easily as it allows for black holes. The equations don't care if time runs forward or backward. A black hole playing in reverse is mathematically a white hole. The billion-dollar question, of course, is whether they actually exist. We have overwhelming observational evidence for black holes, but we have never detected a single white hole. There's a compelling reason for this. A white hole would be an incredibly unstable object. Imagine trying to hold a basketball underwater. The moment you let go, it violently rockets to the surface. A white hole would be like that, but on a cosmic scale. It would be an event of unimaginable energy, and most physicists believe that any such object would almost instantly collapse under the influence of the matter and radiation around it, likely transforming into a black hole almost immediately after its birth. However, one fascinating idea suggests we might have already seen them. Some theorists have proposed that the Big Bang itself could be thought of as a primordial white hole, the ultimate outburst that created our entire universe from a singular point. This idea connects to an even more profound possibility, that a black hole's death might give birth to a white hole. We discussed Hawking radiation, how a black hole slowly evaporates over trillions of years. But what happens when it shrinks to a microscopic size? Some quantum gravity models suggest it doesn't just vanish. Instead, the extreme quantum pressures at its core could cause a dramatic rebound. The collapsing singularity could hit a quantum wall and bounce, turning the entire black hole inside out. The event horizon would transform from a point of no entry into a point of no exit, and the black hole would become a white hole, spewing back out all the information it had consumed over its immense lifetime. This would be an elegant solution to the information paradox, as the information wouldn't be lost at all, just stored for an astronomically long time before being released. Of course, this white hole would be microscopic and would evaporate almost instantly, making it nearly impossible to detect, leaving the idea firmly in the realm of theory for now. Now, let's twist this idea even further, from a cosmic outlet to a cosmic shortcut. This brings us to wormholes, perhaps the most tantalizing concept in all of theoretical physics. Officially known as Einstein-Rosen bridges, a wormhole is a hypothetical tunnel through the very fabric of spacetime. Picture the universe as a vast sheet of paper. To get from a point on one side to a point on the other, you'd have to travel across the entire sheet. But if you could fold the paper so the 2 points touch, a wormhole would be a pencil hole punched through the folded sheet, creating a shortcut that connects 2 distant locations instantaneously. It's a bridge that could, in theory, connect not just different places but different times or even different universes. The mathematics for this is once again embedded within general relativity. The solution that describes a simple black hole, if extended, naturally includes a wormhole tunnel that connects to a hypothetical white hole elsewhere. However, this is where the harsh realities of physics crash the party. There are 2 monumental problems with wormholes: stability and traversability. The kind of wormhole that appears in the simplest equations is what physicists call a non-traversable wormhole. It would be incredibly unstable, pinching off into a singularity faster than the speed of light, meaning nothing, not even a photon, could ever make it through. It would snap shut the instant it formed. To create a wormhole that a person or a spacecraft could actually travel through, you would need a truly exotic ingredient, something with negative energy density, often referred to as exotic matter. This isn't just antimatter. Antimatter has positive energy. Exotic matter would have the bizarre property of repelling gravity instead of attracting it. You would need to line the throat of the wormhole with this substance to prop it open, to keep the gravitational forces from crushing it shut. While tiny amounts of negative energy can be created in lab experiments through quantum effects like the Casimir effect, the quantities needed to stabilize a wormhole large enough for human travel are astronomical, far beyond anything we can conceive of creating. Furthermore, even if you could stabilize it, the mere act of sending a single photon through the tunnel might be enough to trigger a catastrophic feedback loop that collapses it. So, while white holes and wormholes remain enchanting possibilities that emerge directly from Einstein's theory of gravity, they are currently trapped in the realm of mathematical elegance, waiting for a deeper theory of quantum gravity to tell us if they can ever be more than a beautiful dream. They represent the ultimate what-if of cosmology, challenging our understanding of causality, connectivity, and the very structure of the cosmos. They force us to ask if the universe allows for such profound shortcuts, or if these bridges are merely mirages in the desert of equations, beautiful to behold but impossible to ever cross. Yet for all their theoretical grandeur, the black holes we have discussed so far are, in a cosmic sense, relatively small. They are the remnants of dead stars, typically weighing a few times the mass of our Sun. But scattered throughout the universe, lurking at the very centers of galaxies, are true monsters. These are the supermassive black holes, behemoths with masses millions or even billions of times greater than our Sun. And their existence presents us with one of the most urgent and puzzling mysteries in modern cosmology. How did they get so big, so fast? We now have compelling evidence that these giants were already in place when the universe was astonishingly young, a discovery that pushes our theories of cosmic evolution to their absolute limit. Consider the timeline. The Big Bang occurred approximately 13.8 billion years ago. The first stars and galaxies began to coalesce a few 100 million years after that. But the James Webb Space Telescope, our most powerful window into the early cosmos, has recently observed fully formed galaxies with bright, active cores quasars powered by supermassive black holes, all when the universe was less than 1 billion years old. That is a cosmic heartbeat. For a black hole to grow to several billion solar masses in such a short amount of time, it would have to consume matter at an almost unimaginable rate, a rate that pushes against fundamental physical limits known as the Eddington limit. This is the point where the radiation blasting out from the infalling matter becomes so intense that it actually pushes other material away, effectively putting a cap on how quickly a black hole can feed. It is like trying to fill a bucket with a fire hose. The force of the water splashes most of it back out. To reach the masses we observe so early, these black holes must have either started from incredibly massive seeds or found a way to feast in a super Eddington frenzy, defying our standard models of growth. This brings us to the heart of the mystery, the origin of the seed. What was the initial kernel that eventually grew into a galactic giant? Theorists have proposed several compelling yet distinct pathways. The first is the direct collapse model. Imagine the early universe not yet filled with the brilliant light of stars, but instead dominated by vast, pristine clouds of hydrogen and helium gas. Under the right conditions, a gigantic gas cloud, perhaps hundreds of thousands of times the mass of our Sun, could collapse directly under its own weight. But here is the crucial part: it would collapse without ever fragmenting into stars first. To do this, the gas cloud must remain relatively cool. If it gets too hot, it would fragment into many smaller clumps, forming a star cluster instead of a single massive object. Scientists believe this required a specific environment, one bathed in the intense ultraviolet light from nearby, newly formed galaxies. This light would prevent the gas from cooling too much by breaking apart the hydrogen molecules that help it shed heat. The result would be a cataclysmic collapse directly into a heavy seed black hole, a behemoth starting weight of 10,000 to 100,000 solar masses. This gives the black hole a colossal head start, allowing it to reach supermassive proportions within the tight time frame of the early universe. A second, more gradual theory suggests that the seeds were simply the first generation of stellar black holes, but ones born from truly monstrous stars. The very first stars, known as population 3 stars, were not like the stars we see today. They were composed only of hydrogen and helium, and they are thought to have been colossal, perhaps several hundred times the mass of our Sun. Such massive stars burn ferociously bright and die young, in just a few million years, collapsing into black holes of tens or maybe 100 solar masses. This is the light seed scenario. The challenge here is the race against time. Can a 100 solar mass black hole grow by accreting gas and merging with others to become a billion solar mass monster in less than a billion years? It would require nearly continuous feeding at the absolute maximum theoretical rate, a precarious and efficient process that some simulations suggest is possible but difficult. It is like trying to grow an oak tree from an acorn overnight. You would need absolutely perfect, uninterrupted conditions. A third and far more exotic possibility is that the seeds did not form from stars at all. They might be primordial black holes created not by stellar death, but by the extreme densities and pressures in the very first moments after the Big Bang. Tiny fluctuations in the newborn universe could have caused some regions to become so dense that they collapsed directly into black holes. These primordial black holes could have a wide range of sizes, from microscopic to thousands of solar masses. If a significant number of asteroid mass or larger primordial black holes were forged in the Big Bang, they could have served as the perfect seeds for the supermassive black holes we see today. Some scientists have even speculated that dark matter, the invisible stuff that makes up most of the matter in the universe, could be composed of vast numbers of these small primordial black holes, though this remains a highly speculative idea. This is where the revolutionary data from the James Webb Space Telescope is turning from a gentle nudge into a forceful shove. Webb's unparalleled infrared vision allows it to see the light from the very first galaxies, and what it is finding is both breathtaking and deeply challenging. It has identified more early galaxies with bright, active black holes at their cores than most models predicted. Furthermore, some of these black holes appear to be far more massive relative to their host galaxies than those we see in the modern universe. In today's cosmos, the mass of the central black hole is typically about 1,000th of the mass of the galaxy's central bulge of stars. But in the infant universe, the black holes seem to be disproportionately large. This suggests that the black holes may have formed first, and the galaxies assembled around them later, flipping our traditional understanding of galaxy evolution on its head. The black hole wasn't just a feature of the galaxy. It may have been the foundation, the gravitational anchor around which the entire galactic structure coalesced. Each piece of new data from Webb and other observatories helps us weigh these competing theories. The prevalence of these early giants seems to favor the direct collapse model, as it provides the massive head start needed. However, the light seed model is not completely ruled out, especially if we discover that the early universe was far more efficient at feeding black holes than we thought, perhaps through dense, chaotic streams of cold gas that could bypass the Eddington limit. The primordial black hole idea remains a wild card, a solution that connects the birth of black holes to the birth of the universe itself. The origin of supermassive black holes is therefore not just a question about specific objects. It is a question about the fundamental conditions of the early cosmos. Solving it will tell us about the formation of the first stars, the assembly of the first galaxies, and the very nature of the universe in its fiery infancy. These cosmic giants are not merely residents of galaxies, they are living fossils holding the secrets to how everything we see today first began to take shape. While the supermassive black holes command attention with their immense scale, the most profound transformation in our understanding of these objects came from contemplating the very smallest possibilities. This brings us to our sixth mystery, a concept so revolutionary it earned its discoverer a Nobel Prize and overturned the long-held belief that black holes are eternal, Hawking radiation. The story begins with a seemingly unbreakable rule: nothing escapes a black hole. But Stephen Hawking, in a brilliant fusion of general relativity and quantum mechanics, realized this rule has a fascinating loophole, one that exists because space is never truly empty. To understand this, we need to venture into the bizarre world of quantum field theory. What we think of as a perfect vacuum isn't really empty at all. Instead, it's a seething, bubbling sea of virtual particles. These are particle-antiparticle pairs that spontaneously pop into existence everywhere in the universe, borrowing energy from the vacuum for an impossibly brief moment, as allowed by the uncertainty principle, before almost immediately colliding and annihilating each other, returning the energy and vanishing. It's a constant, invisible quantum dance happening all around us. Normally, this process is perfectly balanced. The particles appear and disappear without any net effect. But something extraordinary happens when this quantum froth meets the extreme gravity of a black hole's event horizon. Imagine a virtual particle pair flickering into existence right at the precipice. The immense tidal forces can tear the two particles apart before they have a chance to annihilate. One particle falls into the black hole, while the other, its partner, is flung outward into space, escaping completely. From the perspective of an outside observer, the black hole has just emitted a particle. This is Hawking radiation, but there's a catch, a cosmic accounting trick that ensures energy is conserved. The particle that falls into the black hole must have negative energy. This negative energy reduces the total mass and energy of the black hole. So, while the black hole appears to be emitting radiation, it is actually slowly losing mass, shrinking over time. For a large black hole, this process is incredibly slow. A solar mass black hole would take trillions upon trillions of years to evaporate significantly. But for a very small black hole, the story is completely different. This leads to the thrilling and elusive corollary of Hawking's work, the possibility of primordial mini-black holes. While the black holes we know form from the collapse of massive stars, theorists like Stephen Hawking and Yakov Zeldovich proposed that much smaller black holes could have been created in the violent, dense conditions of the very early universe. In the first fraction of a second after the Big Bang, when the entire cosmos was squeezed into an incredibly hot, dense state, random fluctuations in density could have been so extreme that pockets of space collapsed directly into black holes. These wouldn't be stellar mass giants. They could be as small as an asteroid, a mountain, or even a speck of dust. And according to Hawking's equations, the smaller the black hole, the faster it evaporates. A black hole with the mass of a small asteroid would have a temperature of millions of degrees and would emit radiation furiously, leading to its complete evaporation in a timescale comparable to the current age of the universe. This presents a tantalizing possibility. Some of these primordial black holes forged in the Big Bang could be evaporating right now. Their final moments would not be a quiet fizzle, but a colossal, explosive flash. As a mini black hole shrinks, its temperature rises, causing it to emit Hawking radiation faster and faster. In the last second of its life, it would release a tremendous burst of high-energy gamma rays and other particles, a signature that, in principle, we could detect. For decades, astronomers have been scouring the sky for such an event, looking for a gamma ray burst that doesn't match the profile of a supernova or a neutron star merger. It would be a perfectly isotropic burst, meaning it would look the same from all directions, a telltale sign of a point-like object detonating. So far, no unambiguous candidate has been found, which in itself is a profound result, placing strict limits on how many of these tiny black holes could exist in our universe. The hunt, however, has evolved. If these mini black holes are out there, they might not be on the verge of explosion. They could be in a stable phase, slowly leaking Hawking radiation that is simply too faint for our current telescopes to pick out from the background noise of the cosmos. Others have proposed that they could be detected indirectly through their gravitational influence. If a primordial black hole passed through our solar system, its gravity would subtly perturb the orbits of planets and asteroids. Or if one passed between us and a distant star, its gravity would act as a lens, causing the star's light to briefly magnify in a phenomenon called gravitational microlensing. Several surveys are actively searching for such microlensing events, and while they have found numerous mysterious, unseen objects, none have been definitively identified as a primordial black hole. The failure to find them is as scientifically valuable as a discovery would be. It tells us that the early universe might not have been as chaotic as some models suggest, or that the density fluctuations were smoother than predicted. It also helps narrow down the possible candidates for dark matter. While it now seems unlikely that all dark matter is made of primordial black holes, a significant fraction of it could still be hiding in these ancient relics. The search for Hawking radiation and its primeval sources remains one of the great observational challenges in physics. It is a quest to witness a quantum effect on a cosmic scale, to find the ghostly signature of a theory written in the explosions of black holes that are not born from dead stars, but from the birth pangs of the universe itself. Detecting one would be a direct window into the conditions of the Big Bang and a spectacular confirmation of one of the most profound ideas in modern theoretical physics. But what of the travelers on this one-way journey? We have crossed the event horizon with our hypothetical astronaut and explored the exotic physics of the boundary, but we must now follow that matter inward to its ultimate fate. This is perhaps the most visceral of all the mysteries, the final chapter for anything that ventures too close. According to the classical picture painted by general relativity, the destiny of infalling matter is both simple and horrifying. Once across the horizon, the pull of gravity becomes overwhelming and inexorable. Every particle, every atom, is subjected to increasingly fierce tidal forces. The difference in gravity between your head and your feet becomes so extreme that you are stretched into a long, thin stream of subatomic particles, a process vividly termed spaghettification. There is no force in the universe that can stop this descent. All paths lead inward, and after a finite amount of time, perhaps only seconds or minutes for a stellar mass black hole, this stream of elementary particles arrives at the very center, the singularity. And here, according to Einstein's theory, it simply ceases to exist. The mass, the energy, the very information that defined those particles is crushed into an infinitely dense point, erased from our universe. The story ends at a place where physics itself has no meaning. Yet, as we have seen, quantum mechanics refuses to accept this oblivion. The information paradox demands that the story of that matter cannot be so finally deleted. This conflict gives rise to radically different proposals for what truly happens inside, each one more fantastical than the last. The first major alternative is the holographic principle, which we touched upon earlier. In this view, the fate of matter is not to travel to the center at all. Instead, the moment it crosses the event horizon, its information is instantly scrambled and encoded onto the two-dimensional surface of the horizon itself, like a photon being absorbed by a photographic plate. The three-dimensional journey inward, the spaghettification, the plunge toward the singularity, all of it is an illusion. The interior of the black hole, in a sense, does not exist as a real physical space. It is a projection, a holographic reconstruction created from the data stored on the horizon's surface. The matter, in terms of its information content, never makes it past the gate. It is smeared across the boundary, and its information is slowly leaked back out to the universe over eons via Hawking radiation. In this scenario, the singularity might not even be a real place, but merely a mathematical artifact of an incomplete theory. A second, equally mind-bending possibility involves the very structure of spacetime within the black hole. Some solutions to the equations of general relativity suggest that the interior is not a static chamber of doom, but a dynamically evolving landscape. As you fall inward, space and time undergo a profound switch. Outside the black hole, time moves forward and you have freedom of movement in space, but inside, the roles reverse. The direction toward the singularity becomes your future. It is no longer a place you can choose to move toward or away from. It is a moment in time that you are inevitably traveling toward, just as you are inevitably traveling toward tomorrow. In this view, the singularity is not a point in space you crash into, but a moment in time when the curvature of spacetime becomes infinite, the end of time itself. The fate of matter, then, is to reach the end of its timeline. What happens then? The equations break down, leaving us with a profound question mark. Does the universe simply end for that matter, or does the extreme quantum gravity at that final moment open a doorway to something new? This leads directly to the third and most speculative fate, transuniversal ejection. If the black hole's singularity can be connected to a white hole via a wormhole, as some mathematical models allow, then matter falling in might not be destroyed at all. Instead, it could be funneled through a tunnel in spacetime and Einstein-Rosen bridge, and ejected into another region of our universe, or even into an entirely separate universe. In this incredible scenario, a black hole in our cosmos would act as a gateway, and the white hole in another cosmos would be the source of a mysterious, inexplicable eruption of energy and matter. Your fate would not be annihilation, but cosmic teleportation on the grandest possible scale. While this idea is a mainstay of science fiction, it faces immense physical challenges, primarily the instability of such wormholes. Yet, it remains a tantalizing mathematical possibility that some theories of quantum gravity, like loop quantum gravity, have revived in a new form, suggesting a quantum bounce at the core could transform a black hole into a white hole. Ultimately, the fate of matter is inextricably linked to the two greatest puzzles we have already discussed: the nature of the singularity and the resolution of the information paradox. If the singularity is a real point of infinite density, then destruction is the likely outcome. If it is replaced by a region of quantum fuzz, matter might be transformed into a new, exotic state. If the holographic principle is correct, then the interior journey is an illusion and information is preserved on the surface. We cannot observe any of this directly, so physicists are forced to look for indirect clues. The patterns in Hawking radiation, if we could ever detect and decode them, might hold the answer. The specific way in which information is imprinted on that radiation would tell us a great deal about how and where the black hole stored it, whether it was smashed into a singularity, painted on a holographic surface, or perhaps even sent elsewhere entirely. The fate of matter inside a black hole is therefore more than a question about a particular object. It is a fundamental inquiry into whether the universe allows for true annihilation, or if every story, no matter how seemingly lost, is ultimately preserved in the cosmic ledger. We have followed matter as it crosses the event horizon and confronted the enigma of its ultimate fate, but this journey leads us directly to one of the most profound conceptual leaps in modern physics: the realization that black holes are not just gravitational monsters, but also thermodynamical objects. This connection unlocks our eighth mystery, one that fundamentally reshapes our understanding of information and reality itself. The story begins in the early 1970s when a young physicist named Jacob Bekenstein made a startling proposal that seemed at first to be a violation of common sense. He suggested that black holes must have entropy. In everyday terms, entropy is a measure of disorder or randomness. The second law of thermodynamics, one of the most sacred principles in science, states that the total entropy of a closed system always increases over time. It's why a hot cup of coffee cools down in a room, spreading its heat energy into the more disordered state of the surrounding air. It's why you can scramble an egg, but you can't unscramble it. Now, imagine you have a box filled with a complex, high-entropy gas, a chaotic mess of molecules, each with their own unique information. If you throw that entire box into a black hole, it vanishes from our universe. According to classical general relativity, the black hole's only properties are its mass, charge, and spin. It has no hair, as the saying goes, meaning it retains no other details about what fell in. So, from the perspective of the outside universe, a highly ordered, complex system has disappeared into a perfectly featureless object. The total entropy of the universe appears to have decreased, a direct violation of the second law. This was the puzzle Bekenstein sought to solve. His brilliant insight was that if the second law is to be preserved, the black hole itself must possess an enormous amount of entropy. When the box falls in, the increase in the black hole's entropy must compensate for, and indeed exceed, the loss of the entropy from the box that vanished. This was a radical idea. What could entropy possibly mean for an object that was supposedly a perfect vacuum described only by its mass? The answer came when Einstein, building on work by Stephen Hawking and others, found a formula for this entropy. It was not proportional to the volume of the black hole, as one might intuitively expect for a container of information. Instead, it was proportional to the surface area of its event horizon. The entropy of a black hole is measured in bits of information, and the number of bits is exactly equal to a quarter of the area of the horizon measured in tiny units called Planck areas. This is a staggering result. It implies that the maximum amount of information you can store in a region of space is not determined by how big it is on the inside, but by the size of its surface area. To grasp how strange this is, think of your own brain. It is a three-dimensional object. You would assume its capacity to store memories and information is related to its volume. But the black hole formula suggests that for a given region of space, the ultimate information storage limit is set by painting that information on a two-dimensional surface surrounding it. It is as if the entire three-dimensional interior is nothing but a projection, an illusion, and the true reality is a holographic film on the boundary. This is not just an analogy, it is the birth of the holographic principle, a concept that has since transcended black hole physics to become a potential cornerstone of a theory of quantum gravity. The holographic principle, most famously developed by Leonard Susskind and Gerard T. Hooft, proposes that our perception of a three-dimensional universe is a holographic illusion. All the information needed to describe everything within a volume of space, every star, every planet, every person, is actually encoded on a two-dimensional surface at its boundary. A black hole is the ultimate test case for this principle because it is the simplest object that already obeys this rule. The event horizon is that boundary. The information about every atom, every book, every civilization that ever fell into the black hole is not lost inside the singularity. It is smeared and encoded across the horizon's surface. The black hole's interior, with its terrifying singularity and warped spacetime, is not the primary reality. It is a holographic reconstruction generated from the data on the surface. This idea finds its most concrete realization in string theory through the work of Juan Maldacena, who discovered a precise mathematical duality known as the anti-de Sitter/conformal field theory correspondence, or AD-S/CFT. This provides a full holographic description where a gravitational theory in a bulk volume of space is completely equivalent to a non-gravitational quantum field theory living on its boundary. A black hole in the bulk volume is described by a hot, dense state of quantum particles on the boundary. The physics is identical. You can calculate the same outcomes using either description. This is not just a philosophical statement. It is a working mathematical tool that physicists use to solve problems in quantum gravity that are otherwise intractable. The implications of this are universe-shattering. If the holographic principle is correct, then the world we experience, the three spatial dimensions of height, width, and depth, is an emergent property. It is not fundamental. The true, fundamental laws of physics operate in a lower dimensional realm without gravity. Gravity and the dimensionality of space are themselves emergent phenomena, arising from the complex interactions of quantum information on a distant surface. This radically simplifies the quest for a theory of everything. Instead of trying to quantize gravity in 3 dimensions, we might only need to understand the quantum physics of a 2-dimensional world. The black hole, by forcing us to confront the paradox of information and entropy, has handed us a map suggesting that the universe is far stranger and potentially far simpler than we ever dreamed. It hints that we are all, in a very literal sense, living in a hologram. This elegant simplicity, this idea that a black hole can be described by just 3 numbers, is one of the most remarkable features predicted by general relativity. It is formally known as the no-hair theorem. Think of it this way: if you were to describe a person, you might list their height, weight, and eye color. But that tells you very little about their life story, their memories, or their personality. In the same way, the no-hair theorem suggests that a black hole forgets almost everything about the objects that formed it. It doesn't matter if it was born from a star made of pure hydrogen or from a chaotic mix of planets, asteroids, and spaceships. Once the event horizon forms, all of that intricate detail is erased. The resulting black hole is characterized only by its mass, its electric charge, and its angular momentum or spin. A black hole has no hair, a metaphor meaning it has no other distinguishing features, no frizz or fuzz of complexity. It is the universe's ultimate blank slate, a perfectly featureless abyss. This theorem rests on the powerful foundations of Einstein's theory of gravity. The equations of general relativity are so deterministic and powerful that they dictate that any irregularities, any asymmetry in the collapsing matter, are radiated away as gravitational waves during the black hole's formation. What's left behind is a perfectly smooth, bald object. It's a beautiful and compelling idea, a triumph of mathematical elegance, but this very elegance creates a direct and explosive conflict with quantum mechanics. The quantum world is built on the principle that information is never lost. Every particle has a unique quantum state, and the history of those states should, in principle, be recoverable. The no-hair theorem seems to suggest the opposite, that black holes are cosmic shredders, permanently destroying the information of whatever falls in. This is the information paradox in another guise, highlighting the fundamental rift between our 2 best descriptions of reality. The question then becomes, is the no-hair theorem an absolute truth, or is it an approximation that breaks down when we consider quantum effects? Could black holes have a subtle kind of hair after all? This is not about literal strands, but about the possibility that black holes might retain some faint imprint, some hidden structure that encodes information about their history. Recent theoretical work has begun to challenge the classical picture. Some physicists propose that when you add certain fields from quantum field theory, like scalar fields which are associated with particles like the Higgs boson, black holes can develop what's called soft hair. This isn't hair you could see or touch. It consists of zero-energy excitations on the event horizon, incredibly subtle vibrations that could, in theory, store bits of information. These would be like ghostly fingerprints left on the horizon by infalling matter, a faint memory that the black hole is not entirely bald. But how could we possibly test this? We cannot send a probe into a black hole to check for hair. The answer may lie in observing the most violent events in the universe, black hole mergers. When 2 black holes spiral toward each other and finally collide, they create ripples in spacetime called gravitational waves. The signal from such a collision has a very specific profile. There's the intense chirp as the black holes orbit faster and faster, culminating in a tremendous crash as they merge. But immediately after the merger, the signal doesn't just stop. The newborn, highly distorted black hole rings down, vibrating like a struck bell as it settles into a stable, smooth state. According to the no-hair theorem, this ringdown should be incredibly pure. It should consist only of tones and dampening rates determined exclusively by the final black hole's mass and spin. Its only 2 relevant properties, charge, is thought to be negligible in astrophysical black holes. Any other hairs or hidden structures would introduce additional, subtle frequencies into this ringdown signal. This makes the post-merger ringdown a powerful cosmic test. By carefully analyzing the gravitational wave data from events detected by observatories like LIGO and Virgo, scientists can search for deviations from the pure tones predicted by the no-hair theorem. Finding an extra frequency, an unexpected echo, or a different rate of decay would be like hearing a bell ring with a slight buzz or a warble, a clear sign that the bell is not perfectly smooth. It would be direct evidence that the final black hole is not the simple, three-propertied object we thought it was. It would suggest that some information about the pre-merger black holes, perhaps their individual spins or masses in a more complex way, is preserved on the horizon of the merged object. A confirmed detection of such an anomaly would be a monumental discovery, forcing a revision of the no-hair theorem and providing the first observational clues about how information might be preserved by black holes. The silent ringing of these cosmic bells across the universe may be whispering the secrets of what black holes truly remember. The elegant simplicity of a black hole, defined only by its mass, spin, and charge, is a direct result of a cosmic rule that many physicists believe must exist. But what if that rule could be broken? This brings us to a thought so unsettling that it has its own dramatic name, the cosmic censorship hypothesis. Proposed by the legendary physicist Roger Penrose, this is not a formal proof but a deeply held conviction, a bet on the good behavior of the universe. It suggests that nature abhors a naked singularity. The hypothesis posits that every singularity, every point of infinite density where the laws of physics break down, must always be hidden from view, forever cloaked behind the protective veil of an event horizon. It's as if the universe has a built-in censorship board, ensuring that the ultimate chaos and paradox of the singularity can never leak out and infect the rest of reality. The event horizon acts as a cosmic curtain drawn across a stage where the play no longer follows any known script. Now imagine that curtain being ripped away. The result would be a naked singularity, an object of infinite density exposed for the entire universe to see. This is not merely a black hole without its event horizon. It is a rupture in the fabric of spacetime itself, a place where gravity becomes infinite, where time may stop or run backward, and where the deterministic laws of cause and effect we rely upon simply cease to function. A naked singularity would be a gateway to pure unpredictability. Light could escape from its immediate vicinity, meaning we could, in theory, observe this point of ultimate lawlessness. The implications are staggering. If you could see a naked singularity, you could potentially witness events for which there is no cause, or where effects precede their causes, violating the fundamental principle of causality that underpins all of physics. It would be like watching a movie where the ending happens before the beginning, and the characters can change the plot at will. The very foundation of scientific prediction, the idea that the universe operates by consistent, knowable rules, would be thrown into question. So, how could such a monstrous object come to be? The most widely discussed theoretical pathway involves taking a standard black hole and pushing it past its limits. According to the no-hair theorem, a black hole is defined by just three parameters, and one of them is spin. Black holes can rotate, some at velocities approaching the speed of light. There is a theoretical maximum to how fast they can spin before their structure fundamentally changes. If you could feed a black hole a precise amount of matter with just the right angular momentum, you might, in theory, overspin it. The idea is that the additional rotational energy would not increase the size of the event horizon proportionally, but could instead disrupt it. If the spin parameter becomes too large relative to the mass, the calculations of general relativity suggest the event horizon could vanish, leaving the central singularity exposed and naked. Another speculative scenario involves the collision of two black holes. In the violent tumult of a merger, the complex, dynamic distortions of spacetime might, for a fleeting moment, pinch off or tear the event horizon before it can re-establish itself, briefly revealing the singularities within. Yet, despite these theoretical possibilities, we have never observed a naked singularity. This fact is the strongest argument for the cosmic censorship hypothesis. The universe seems to protect itself from such paradoxes. There may be a host of physical processes that act as cosmic regulators. For instance, when you try to overspin a black hole, the very act of throwing matter into it might generate incredible amounts of radiation or cause the black hole to shed energy in a way that prevents it from ever reaching the critical point. The universe might have a kind of cosmic immune system that instantly forms a new event horizon or otherwise cloaks the singularity whenever it is threatened with exposure. The search for naked singularities is not just an academic exercise, it is a direct test of whether the universe is fundamentally predictable. Their continued absence from our observations suggests that Penrose's bet on cosmic censorship is correct, that the universe is indeed an orderly place where the most extreme pathologies are safely quarantined behind unsurpassable boundaries. The silence of the cosmos on this front is in itself a profound message about the nature of physical law. But if the holographic principle offers a ghostly, ethereal solution to the information paradox, another proposed answer is far more violent and confrontational. This is the black hole firewall paradox, a concept so dramatic it suggests the event horizon is not the serene gateway of Einstein's imagination, but a searing inferno. The story of the firewall begins with a desperate attempt to rescue quantum mechanics from the threat of information loss. We are forced to make a stark choice between three deeply cherished principles of physics, and accepting the firewall means sacrificing one of Einstein's greatest insights. Recall the core of the information problem. Stephen Hawking showed that if black holes evaporate completely via random Hawking radiation, the information about what fell in is lost forever, violating a fundamental rule of quantum theory. To save this rule, the information must somehow be encoded in the radiation that escapes. But for this to work, a subtle but crucial property of quantum mechanics called entanglement must be manipulated in a way that creates a catastrophe. To understand this, we need to look at the quantum particles at the horizon. The pair of virtual particles that appears, one falls in and one escapes as Hawking radiation. Initially, these two particles are deeply entangled, a quantum connection that is stronger than any classical link. The escaping particle is also entangled with its partner that fell in long ago, which is now deep inside the black hole. This is the problem. A fundamental rule of quantum mechanics, often called the monogamy of entanglement, states that a particle cannot be fully entangled with two different systems at the same time. It's like a quantum love triangle. You can't be maximally committed to two partners. For information to escape, the newly escaped Hawking particle must become entangled with the radiation that left earlier, so that together they carry an encoded story of the black hole's content. But for the infalling astronaut to experience a smooth horizon as Einstein predicted, the escaped particle must still be entangled with its infalling partner. It's an impossible demand. The particle cannot be entangled with both the early radiation and its infalling partner. Something has to give. In 2012, a group of physicists led by Ahmed Olmary, Donald Maroff, Joe Polchinski, and James Sully, now known by their initials AMPS, argued that the only way to preserve the information is to sever the entanglement between the particle pairs right at the horizon. The moment this entanglement is broken, it releases a tremendous amount of energy. The result, the event horizon transforms into a blazing curtain of high-energy particles, a firewall. Anything or anyone falling into the black hole would not experience a gentle descent into darkness. They would be instantly vaporized upon contact with this wall of fire. The argument for a firewall is brutally logical. It prioritizes the preservation of quantum information above all else. If information is never lost, and if the monogamy of entanglement is an unbreakable law, then the smooth horizon of general relativity must be an illusion. The firewall becomes the mechanism that scrambles the information and imprints it onto the Hawking radiation, ensuring it is returned to the universe. In this view, the paradox is resolved by accepting that Einstein's description of the horizon is only an approximation, one that fails when quantum effects become paramount. The arguments against the firewall, however, are equally powerful, rooted in the profound success of general relativity. The main objection is that it blatantly violates Einstein's principle of equivalence, a cornerstone of his theory. This principle assures us that a freely falling observer will not feel any special forces as they cross the event horizon. They should be in a state of weightless free fall, unaware of their point of no return. A firewall shatters this principle completely. Instead of a smooth transition, the horizon becomes the most violent place in the universe. Furthermore, from the perspective of an outside observer, it would take an infinite amount of time for an object to actually reach the horizon due to the extreme gravitational time dilation. So, from our viewpoint, the falling astronaut would appear to slow down, freeze, and be redshifted out of existence at the horizon, never even crossing it to hit the firewall. This creates a bizarre contradiction. Does the astronaut get incinerated or don't they? The answer seems to depend on your point of view, which is an unacceptable situation in physics. The firewall paradox therefore leaves us with a trilemma, a choice between three seemingly true but mutually exclusive statements. First, information is not lost. Second, quantum field theory works as expected for an infalling observer, meaning they see no firewall. And third, an infalling observer can verify that the escaping radiation is entangled with the radiation inside the black hole. You can hold any two of these statements to be true, but the third must be false. The AMP's argument chooses to sacrifice the second statement, accepting the firewall. Others have proposed ways to save the smooth horizon, perhaps by finding a loophole in the monogamy rule, or by suggesting that the interior of the black hole is so complex that the required measurements are impossible in practice. The firewall remains a highly controversial but critically important idea because it crystallizes the conflict between general relativity and quantum mechanics into a single, stark question about what happens at the most important boundary in the universe. It forces physicists to confront the possibility that our most intuitive picture of space and time might break down in the most dramatic way imaginable, not with a quiet whimper, but with a cosmic roar of fire. We have explored the violent paradox of firewalls and the cosmic censorship that may hide the worst infinities, but these puzzles exist within the framework of a universe whose dominant components remain completely mysterious. This leads us to a question that bridges the very large and the very small. What is the relationship between black holes and the dark sector of the universe? The cosmos, we have learned, is not primarily made of the stars, planets, and gas that we see. Over 95% of its content is in the form of dark matter and dark energy, invisible substances that we can only detect through their gravitational effects. It is a profound embarrassment for modern physics that we do not know what these entities are. Black holes, as the most extreme gravitational laboratories, might just hold the key. Let's start with dark matter. We know it exists because galaxies rotate too fast to be held together by the gravity of their visible stars alone. There must be a huge halo of unseen matter providing the extra gravitational glue. The leading candidate for decades has been a hypothetical particle, something like a WIMP or weakly interacting massive particle, but despite extensive searches, no such particle has been found. This failure has opened the door to a more dramatic possibility, that a significant portion of dark matter is not a sea of tiny particles, but a population of ancient black holes. These would be the primordial black holes we discussed earlier, those that could have formed from density fluctuations in the very early universe. If vast numbers of these primordial black holes were created with masses in a certain range, say, from the mass of a small asteroid up to dozens of solar masses, they could be floating invisibly throughout galaxies, including our own, providing the gravitational pull we attribute to dark matter. The appeal of this idea is its elegance. It solves two mysteries with one object: the nature of dark matter and the origin of some black holes. We wouldn't need to invent a new, never-before-seen particle. We would just need to find black holes that form through a non-stellar process. However, this proposal faces severe constraints from observations. If the universe were swarming with enough asteroid-mass primordial black holes to account for all dark matter, they would frequently pass between Earth and distant stars. Their gravity would act as a lens, causing the star's light to briefly magnify in a phenomenon called gravitational microlensing. Surveys like OGLE and HSC have extensively monitored millions of stars for such events. While they have found some intriguing lensing candidates, there are simply not enough to account for 100% of the dark matter. The same is true for planetary mass black holes. They are not abundant enough. What about larger ones in the stellar mass range? The groundbreaking observations by the LIGO and Virgo gravitational wave observatories have provided crucial data here. They have detected the mergers of many black hole pairs, some surprisingly heavy. Could these be primordial black holes making up the dark matter? Again, the numbers don't quite add up. If the dark matter halos of galaxies were packed with such black holes, their frequent interactions and mergers would produce many more gravitational wave signals than we currently observe. Furthermore, the presence of so many massive, compact objects would disrupt the delicate structures of star clusters and dwarf galaxies in ways that we do not see. The observational evidence has effectively ruled out the possibility that primordial black holes constitute all of the dark matter. However, a fascinating window remains open. They could still make up a percentage of it, perhaps a few percent, or even a significant fraction if their mass falls into a specific, narrow window that is harder to constrain, such as between 20 and 100 solar masses. The hunt is now on to determine if this dark matter fraction is real, with astronomers using every tool available to scour the cosmos for these elusive ancient ghosts. While dark matter pulls the universe together on galactic scales, dark energy does the opposite on cosmic scales. Discovered in the late 1990s, dark energy is the name we give to the mysterious force causing the expansion of the universe to accelerate. It acts as a kind of anti-gravity, pushing galaxies apart from one another. Its nature is arguably the greatest puzzle in all of cosmology. What does this have to do with black holes? At first glance, very little. A black hole's gravity is intensely local, dominating its immediate surroundings, while dark energy's effect is only apparent across the vast, empty distances between galaxy clusters. But when we look at the largest black holes, the supermassive ones at the centers of galaxies, a potential connection emerges. As the universe expands due to dark energy, these black holes are embedded within that expanding space. Some sophisticated theoretical work suggests that as a black hole sits in this accelerating cosmos, it may actually gain mass very slowly, in tandem with the growth of the cosmic horizon driven by dark energy. It's a subtle effect, but it hints at a deep, fundamental link between the physics of the largest scales and the properties of the most compact objects. This leads to even more speculative and thrilling ideas. Could dark energy be related to the vacuum energy of space itself, a concept that emerges from quantum field theory? And if so, does the incredible warping of spacetime inside a black hole alter the properties of that vacuum energy in significant ways? Some highly speculative models propose that the singularity at a black hole's center might not be a point of infinite density in the classical sense, but a portal to a region where the equations of dark energy take over. In this view, the interior of a black hole could be a universe in its own right, undergoing an accelerated expansion. This is part of the black hole cosmology idea, suggesting that what we call the Big Bang was the white hole explosion of a black hole in a parent universe, and that our own universe's expansion is driven by the dark energy that originated from that event. Another fascinating connection involves the cosmological constant, the simplest mathematical description of dark energy. When physicists try to calculate its value from quantum theory, they get a number that is astronomically too large, off by a factor of 1 followed by 120 zeros. This is the worst prediction in the history of science. Understanding the vacuum state around black holes where gravity is ultra-strong might be the key to solving this monumental discrepancy by showing how quantum gravity naturally cancels out most of this energy. Ultimately, the potential links between black holes and the dark universe represent the next frontier in fundamental physics. They force us to consider that the keys to understanding the cosmos's largest-scale behavior, its composition, and its ultimate fate might be hidden in the most extreme gravitational environments. By studying the shadows of black holes with telescopes like the Event Horizon Telescope, by listening to their collisions with gravitational wave observatories, and by searching for the lensing effects of primordial black holes, we are not just learning about these exotic objects. We are conducting a deep probe into the 95% of the universe that currently lies in the dark. Each observation places a new constraint, closes a theoretical door, or opens a new window into the possibility that black holes are not just inhabitants of the cosmos, but are deeply woven into the fabric of its darkest secrets. Yet for all their power to pull matter in, black holes are also capable of the most spectacular cosmic eruptions. This brings us to our 13th mystery, one that showcases their dynamic and paradoxical nature, the mystery of black hole jets. In the darkest corners of space, from the hearts of active galaxies, we see twin beams of energy and matter screaming across the cosmos at nearly the speed of light. These are relativistic jets, and they are among the most powerful and efficient engines in the universe, capable of punching millions of light years through intergalactic space. The sheer scale is almost impossible to comprehend. Imagine a stream of plasma so concentrated and energetic that it extends far beyond the boundaries of its host galaxy, a lighthouse beam on a truly cosmic scale. The central paradox is stark. How can an object defined by its ability to trap everything, even light, simultaneously act as the most powerful particle accelerator we know? We have a general framework for how these jets might work, a recipe that requires 3 key ingredients. First, you need a central engine, a supermassive black hole spinning rapidly. Second, you need fuel, a vast, swirling disk of superheated gas and dust, known as an accretion disk spiraling inward. Third, and most crucially, you need incredibly powerful magnetic fields. As the black hole spins, it drags the fabric of spacetime around with it, an effect known as frame dragging. This motion twists the magnetic fields that are anchored in the accretion disk, winding them up like cosmic rubber bands. Think of it as a gravitational dynamo. The immense rotational energy of the black hole is transferred to these magnetic fields, which become tightly wound and enormously powerful. At the poles of the black hole, where the magnetic field lines are funneled together, this built-up energy can find a release valve. The twisted fields snap, reorganizing themselves in a process called magnetic reconnection, which acts like a slingshot, flinging charged particles outward along the narrow polar axis. The magnetic field also acts as a nozzle, collimating the erupting plasma into a tight, focused beam that can maintain its integrity over staggering distances. This general model is compelling, but the devil, as always, is in the details that we still cannot fully explain. The first major puzzle is the incredible efficiency of the process. These jets can convert the gravitational energy of infalling matter into kinetic energy with an efficiency that can approach 50% or more. To put that in perspective, the nuclear fusion that powers stars is only about 0.7% efficient. A black hole jet is orders of magnitude more effective at turning mass into energy. How exactly does the black hole manage to harness its spin energy so effectively and channel it so perfectly? The second puzzle is the remarkable stability and collimation of the beams. How do they remain so tight and focused for millions of years over distances that dwarf their entire galaxy without spreading out and dissipating? Our models suggest the magnetic fields are the key, but the precise mechanism that provides this long-range stability is still a subject of intense debate. Some theories propose that the jet is actually pinched and confined by the pressure of the very gas and magnetic fields it is moving through, like a stream of water being contained by the walls of a pipe, even in the near vacuum of intergalactic space. This is where revolutionary instruments like the Event Horizon Telescope come into play. The 8, famous for capturing the first ever image of a black hole's shadow in the galaxy Messier 87, is not just taking pretty pictures. It is a forensic tool designed to probe the very region where the jet is launched. The central question is, where does the jet actually begin? Does it originate from the accretion disk itself, far from the event horizon? Or is it launched from the much more extreme environment of the black hole's ergosphere, the region just outside the event horizon where frame dragging is so powerful that nothing can remain stationary? The EHT's unprecedented resolution allows it to peer into this chaotic realm. By studying the polarization of the light near the black hole's shadow, scientists can map the structure of the magnetic fields. The initial results from Messier 87 are stunningly clear. They show a powerful, organized magnetic field near the event horizon, a field with the strength and geometry needed to launch and power the massive jet we see. This strongly suggests that the black hole's spin and its immediate environment are the primary drivers, not just the accretion disk further out, but the EHT is just one piece of the puzzle. Observations across the electromagnetic spectrum, from radio waves to high-energy gamma rays, are crucial. When a jet is pointed nearly toward Earth, we see a phenomenon known as a blazar, an object that flickers and flares with unbelievable intensity. By monitoring these blazars, astronomers can see explosive events happening deep within the jet base, sometimes over timescales of just hours or minutes. These rapid variations tell us that the central engine is incredibly compact and that the processes powering the jets are dynamic and violent. Each flare is a clue, a signal about the physics of particle acceleration and magnetic reconnection happening terrifyingly close to the point of no return. Solving the mystery of black hole jets is not just about understanding one type of cosmic object. It is about understanding how the universe can take the ultimate destructive force and transform it into a creative one, sculpting galaxies, heating vast clouds of gas, and ultimately influencing the rate of star formation across the cosmos. The jets are a testament to the fact that a black hole is not just a grave for matter, but also a cradle for some of the most energetic phenomena in existence. But if supermassive black holes are the giants and stellar mass black holes are the commoners, a crucial question emerges: where are the missing monarchs? Our cosmic family tree of black holes appears to have a glaring gap, an absence of middleweight objects that would bridge the vast chasm between the few solar mass remnants of dead stars and the billion solar mass behemoths at galactic centers. These hypothetical objects are known as intermediate mass black holes, or IMBHS, and their existence, or lack thereof, holds the key to one of the most important questions in galaxy evolution. How did the supermassive black holes get so big so fast? Finding them would confirm a critical pathway for growth, while their continued elusion would force us to rethink our models entirely. The hunt for these cosmic missing links has been long and frustrating. The evidence for their existence is sparse, indirect, and often hotly debated. One of the most promising clues comes from a specific class of incredibly bright objects known as ultraluminous X-ray sources, or ULXS. These are spots in galaxies, usually found away from the galactic center, that pour out staggering amounts of X-ray radiation, far more than could be explained by a typical stellar mass black hole. The brightness of an accretion disk is limited by its own radiation. There's a point where the energy blasting outward pushes back on the infalling gas, creating a balance known as the Eddington limit. A stellar mass black hole simply cannot exceed this limit by a large margin without tearing its own fuel supply apart. So, when we see an object that is 10, 100, or even 1,000 times brighter than this limit, the most straightforward explanation is that we are not looking at a small black hole, but a larger one. A black hole with a mass of a few thousand suns could easily power such an ultraluminous source without breaking a sweat. Several ULXS have been studied intensely, with their X-ray flicker patterns and surrounding gas motions suggesting the presence of a hidden object with a mass in the elusive intermediate range. However, the case is not closed. Alternative explanations persist, such as the possibility that these are stellar mass black holes with unusually focused, beam-like jets pointed directly at us, making them appear deceptively bright, or that they are accreting matter in a super-efficient, super-Eddington state that we don't fully understand. Each candidate is a cosmic crime scene where the suspect, the intermediate mass black hole, has left compelling circumstantial evidence, but a definitive fingerprint has been maddeningly difficult to obtain. A more recent and powerful line of evidence has emerged from the same technology that revolutionized black hole astronomy: gravitational wave detectors. When LIGO and Virgo listen to the cosmic waves from colliding black holes, the frequency of the signal tells them the total mass of the system. The very first detection in 2015 was a landmark, revealing a merger of two black holes, each about 30 times the mass of our Sun, already surprisingly heavy for stellar remnants. But in 2019, a signal named JW1-90521 sent a jolt of excitement through the community. This event appeared to be the merger of two black holes with masses of about 85 and 66 solar masses. The resulting black hole was 142 solar masses, placing it squarely in the intermediate mass range for the first time. This was monumental. It was direct evidence that black holes could form and merge in this mass gap. However, even this discovery came with a twist of mystery. The 85 solar mass progenitor was itself problematic because it falls within what's known as the pair instability mass gap. According to stellar evolution models, stars in a specific mass range should not collapse quietly into black holes. They should be completely obliterated in a pair instability supernova, leaving nothing behind. The existence of an 85 solar mass black hole challenges our understanding of how the most massive stars die. So, while JW1-90521 provided the strongest case yet for an intermediate mass black hole, it also deepened the puzzle of how such an object could have formed in the first place. Why is finding these missing links so crucial? It all comes back to the growth of the supermassive black holes. There are two primary theories for how the giants in the centers of galaxies grew to such immense proportions. The first is the bottom-up scenario, where small seeds, the remnants of the first stars, weighing perhaps a few dozen solar masses, slowly grew over billions of years by merging with each other and voraciously consuming gas. This pathway absolutely requires intermediate mass black holes as stepping stones. You cannot build a billion solar mass giant from stellar mass seeds without going through the intermediate phase. If we can find a population of IMBHS, especially in dwarf galaxies or in the outskirts of larger galaxies, it would be powerful support for this gradual growth model. The alternative is the top-down scenario, where supermassive black holes got a huge head start from direct collapse black holes, born with masses of tens of thousands of suns. In this model, intermediate mass black holes might be much rarer, as the seeds would quickly jump to supermassive status. Therefore, the abundance or scarcity of IMBHS acts as a direct test of these competing theories. They are the living fossils that record the evolutionary history of the most massive objects in the universe. The search is now accelerating using a multi-pronged approach. Astronomers are scrutinizing dense star clusters, both globular clusters that orbit galaxies and young massive clusters within them. These densely packed environments are perfect breeding grounds for IMBHS. Through dynamical interactions, stellar mass black holes could sink to the cluster's center and merge, or a single, larger black hole could form and lurk there, its presence betrayed by the unusual speeds of the stars swirling around it. Measurements of stellar velocities in several clusters have indeed hinted at a central, unseen mass of a few thousand suns, though alternative explanations involving a dense knot of stellar remnants can sometimes explain the data. Beyond star clusters, the next generation of gravitational wave observatories, like the space-based LISA mission planned for the 2030-50s, will be exquisitely sensitive to the mergers of black holes in the intermediate mass range. LISA will be able to hear the low-frequency hum of these collisions across the entire universe, potentially revealing a whole population of IMBHS that are currently invisible to us. The mystery of the missing links is therefore a pivotal one. Finding them would fill a critical gap in our cosmic hierarchy and chart the growth path of galactic giants. Their continued absence would be equally profound, forcing us to concede that the universe has a more exotic, more efficient way of building its most massive structures than we have yet been able to imagine. The silent, invisible fabric of the cosmos has finally begun to speak, and its language is one of ripples and shudders. For decades, black holes existed as theoretical phantoms or silent shadows, inferred from their gravitational influence but never directly witnessed in action. That all changed in 2015 when humanity's ears were opened to the universe. The Laser Interferometer Gravitational Wave Observatory, or LIGO, made history by detecting the faint, ghostly whisper of a gravitational wave, a ripple in spacetime itself, generated over 1 billion years ago by the violent merger of two black holes. This was not seeing in the traditional sense. It was a new form of astronomy, one of hearing. We were no longer just stargazers. We had become listeners to the symphony of spacetime, and the most powerful notes in that symphony are played by colliding black holes. These detections solved one mystery while unveiling a host of new, more profound ones. The very first signal, named GW150914, was a revelation. It revealed two black holes, each about 30 times the mass of our Sun, spiraling together in a final, fatal dance before merging into a single, more massive object. The detection itself was a triumphant confirmation of Einstein's century-old prediction, but the masses of the black holes were immediately puzzling. 30 solar masses is heavy, unusually heavy for a black hole formed from the collapse of a single star. Our models of stellar evolution suggested that black holes from typical stellar deaths should be more in the range of 5 to 20 solar masses. So, where did these heavyweights come from? Were they the remnants of a previous generation of supermassive stars in the early universe, or did they grow to this size by swallowing other objects? Each new merger detected by LIGO and its European counterpart, Virgo, has added another data point, painting a picture that is far more complex and fascinating than we ever anticipated. We now have a catalogue of events, a census of cosmic collisions that reveals a surprising diversity in the black hole population. This diversity forces us to ask a fundamental question about the social lives of black holes. How do they find partners? There are two leading theories for how these binary pairs form. The first is the isolated binary pathway. Imagine two massive stars born together as a binary pair orbiting each other closely. They live their lives burning through their nuclear fuel, and eventually each explodes in a supernova. If conditions are just right, the supernova explosions are not too violent to kick the stars apart, and both leave behind black holes that continue to orbit one another. Over billions of years, they slowly lose energy by emitting gravitational waves, spiraling closer and closer until they finally merge. This is a relatively quiet, predictable life story. The second pathway is far more dramatic and chaotic. It happens in the bustling, crowded environments of dense star clusters, like globular clusters that orbit the halos of galaxies. In these stellar cities, thousands of stars are packed into a relatively small volume of space. Here, black holes, being the most massive objects, will naturally sink to the center of the cluster through a process called dynamical friction. It is a gravitational game of pool. When a heavy black hole passes near lighter stars, its gravity scatters them, and with each interaction, the black hole loses a bit of energy, sinking deeper into the cluster's core. At the center, a whole population of black holes can gather, interacting and exchanging partners in a complex gravitational dance. Through these encounters, two black holes can become gravitationally bound, forming a binary pair that is then ejected from the crowded core. This dynamic formation channel can produce black hole pairs with very different properties than the isolated binary channel. Their orbits might be tilted and eccentric, not circular, and the black holes themselves could be more massive, having grown by consuming other stars or even merging with smaller black holes beforehand. The data from LIGO and Virgo is now allowing us to distinguish between these stories. By studying the precise pattern of the gravitational waves, the chirp that rises in frequency and amplitude as the black holes spiral inward, scientists can infer not just the masses of the objects but also their spins. The spin is a crucial clue. In the isolated binary scenario, you would expect the spins of the two black holes to be aligned with the orbit of the binary system, much like the Earth's rotation axis is roughly aligned with its orbit around the Sun. This is because the two stars were born from the same rotating cloud of gas. However, in the dynamic formation channel, black holes are brought together by random encounters. Their spins would be expected to be randomly oriented, even tilted completely sideways relative to their orbital plane. Some of the events detected so far show hints of these misaligned spins, providing strong, though not yet conclusive, evidence for the chaotic dance of the star cluster pathway. But the surprises did not stop with spin. The event JWST, the merger that created the first clear intermediate mass black hole, presented a double mystery. Not only was the final product in a mass range we thought was rare, but one of the merging black holes weighed in at around 85 solar masses. This mass falls directly into what astrophysicists call the pair instability mass gap. The theory goes that for very massive stars between about 65 and 120 solar masses, the core becomes so hot that it starts producing electron-positron pairs. This process saps the star's internal pressure, leading to a runaway thermonuclear explosion that is so violent it completely obliterates the star, leaving no remnant behind, no black hole, no neutron star, just scattered gas. An 85 solar mass black hole simply should not exist if this theory is correct. Its detection forces us to reconsider the final moments of the most massive stars. Perhaps stellar winds strip away so much mass before the explosion that the star moves out of the forbidden range. Or maybe the pair instability process is not as absolute as we thought, and under certain conditions, a partial collapse can still leave a massive remnant. This one event has sent theorists back to their drawing boards, challenging a key pillar of our understanding of how stars die. Each ripple in spacetime detected here on Earth is a messenger from a cataclysm of unimaginable power, carrying encoded information about the properties and history of the objects that created it. The growing catalogue of mergers is revealing a black hole population that is more diverse, more massive, and formed through more varied pathways than our textbooks predicted. We are learning that the universe is not just populated by solitary black holes, but by families and dynasties of them, interacting, merging, and growing in ways we are only beginning to decipher. This new window of gravitational wave astronomy has not given us all the answers. Instead, it has shown us that the story of black holes is richer, stranger, and more interconnected than we ever dreamed. But if the gravitational waves from colliding black holes give us a soundtrack for their violent mergers, they tell us nothing about the silent, dark journey within. To venture beyond the event horizon is to enter a realm where our maps of space-time are ripped apart, and the very geometry of reality becomes a question mark. We have spoken of the singularity as an endpoint, but what if it isn't the end at all? What if the crushing density at the core doesn't lead to oblivion but to a gateway? This brings us to one of the most tantalizing possibilities in all of theoretical physics, the idea that the interior of a black hole might not be a dead end but a bridge. The mathematics of general relativity in its pure and elegant form offers a startling suggestion. The solution for a simple, non-rotating black hole, known as the Schwarzschild metric, can be mathematically extended. When you follow the equations describing the path of an object falling inward, they don't simply stop at the singularity. Instead, they can be continued, revealing a mirror image of the black hole's interior, a white hole spewing matter outward. Connecting these two regions is a tunnel, a theoretical structure known as an Einstein-Rosen bridge, which we more commonly call a wormhole. In this picture, a black hole in our universe could be one mouth of a tunnel, with the other mouth being a white hole in a completely different region of space-time, or even in a separate universe altogether. The infalling matter would not be annihilated, it would be transported. It's a concept that feels ripped from the pages of science fiction, yet it emerges naturally from the same equations that describe the gravitational field of the Sun. The geometry of such a structure is mind-bending to visualize. Think of our universe as a vast, two-dimensional sheet. To travel from one point to a distant point on that sheet would take an immense amount of time. But if you could fold the sheet so the 2 points touch, a wormhole would be like a short, vertical tube connecting them, creating a shortcut through a higher dimension. Inside the black hole, as you fall toward what you think is the singularity, you would instead find yourself entering the throat of this tunnel. The extreme curvature of space-time would make the journey inward feel like a descent, but the geometry of the bridge would ultimately lead you to an ascent, exiting through the white hole on the other side. For a fleeting moment, the equations suggest the entire universe could be traversed in an instant. However, this is where the harsh realities of physics intervene, transforming this beautiful mathematical dream into a profound physical mystery. The first and most formidable problem is stability. The wormhole described in the simplest black hole solution is what physicists call non-traversable. It is incredibly unstable, akin to a soap bubble. The moment it forms, the tunnel would pinch off at the narrowest point infinitely fast, creating a singularity that would crush anything attempting to pass through. The bridge would snap shut before even a single photon could make the journey. This instability is not a minor technicality. It is a fundamental consequence of the intense gravitational forces that the structure must withstand. The classical equations of general relativity seem to forbid peaceful travel through these cosmic shortcuts. To even dream of a traversable wormhole, you need a truly exotic ingredient, something with negative energy density, often referred to as exotic matter. This isn't just antimatter, which has positive energy and would still be attracted by gravity. Exotic matter would possess a kind of gravitational repulsion. If you could line the throat of the wormhole with this substance, it could, in theory, act as a scaffolding, propping the tunnel open against the crushing forces trying to collapse it. While quantum mechanics allows for the existence of tiny amounts of negative energy in specific circumstances, such as in the Casimir effect, where two closely spaced metal plates experience a slight attractive force due to the suppression of virtual particles between them, the quantities needed to stabilize a wormhole large enough for human travel are astronomical. We are talking about a concentration of exotic matter far beyond anything we can currently conceive of creating or finding in nature. Even if you could somehow solve the stability problem, a second, equally daunting challenge emerges: the manipulation of the wormhole itself. Creating a useful bridge would require placing the two mouths in desired locations. But how do you move a black hole? Furthermore, the mere act of sending a single particle through the tunnel might trigger a feedback effect that destabilizes it. Some calculations suggest that the energy of the traveling particle would cause the wormhole to collapse behind it, severing the connection. The possibility of using these structures for practical time travel introduces even more severe paradoxes, like the famous grandfather paradox, which many physicists believe are forbidden by the laws of causality. So, while the interior geometry of a black hole might mathematically contain a bridge to elsewhere, the physical plausibility of such a journey remains, for now, one of the deepest unsolved mysteries in cosmology. It is a breathtaking idea that lives at the very edge of theoretical possibility, a ghost in the machine of Einstein's equations, reminding us that the universe may hold wonders we can describe mathematically long before we can ever hope to experience them. Now, let's shrink our perspective from the vast dynamical jets and merging giants down to the very edge of reality, to the quantum realm that buzzes with activity just outside the event horizon. This is where the smooth, predictable geometry of Einstein's general relativity collides head-on with the fuzzy, probabilistic chaos of quantum mechanics. The result is a seething, frothing space that challenges our very understanding of the vacuum itself. To grasp this, we must first abandon the idea of true emptiness. What we call a vacuum is not a dead, static void. According to quantum field theory, it is a vibrant sea of potential, constantly simmering with transient fluctuations. Everywhere in the universe, pairs of virtual particles and antiparticles spontaneously blink into existence, borrowing energy from the vacuum for a fleeting moment, only to annihilate each other and vanish back into the nothingness almost instantly. It's a constant, unseeable dance of creation and destruction, a quantum foam that underpins all of reality. Place this quantum foam at the precipice of a black hole, and the serene picture of the event horizon transforms into a scene of frenetic activity. These virtual particle pairs are born everywhere, including right at the edge of the point of no return. In most of space, their existence is so brief it has no net effect. But at the event horizon, the black hole's immense gravity can perform a cosmic heist. It can rip the two virtual particles apart before they have a chance to recombine. One particle falls into the black hole, while its partner is ejected outward, becoming a real particle that carries energy away into the universe. This is the mechanism of Hawking radiation. To conserve energy, the particle that falls in must have negative energy, which effectively reduces the mass of the black hole. This process, repeated across the entire horizon over eons, is what causes black holes to slowly evaporate. But this elegant description hides a deeper mystery about the nature of the horizon itself. Is it truly the smooth, mathematical surface of general relativity, or is it fundamentally altered by this relentless quantum activity? This leads us to a related but distinct phenomenon that highlights the strange role of the observer in this quantum drama, the Unruh effect, proposed by physicist William Unruh. This effect reveals that the concept of a particle is not absolute. It depends on who is looking and how they are moving. An observer accelerating through what they perceive as a perfect vacuum will actually detect a warm bath of particles, a thermal radiation that is completely invisible to an inertial observer floating peacefully. The faster the acceleration, the hotter this perceived bath becomes. Now consider the event horizon. While it is not a physical surface, it represents a point of infinite redshift due to gravity. The relationship between acceleration and gravity, encapsulated in Einstein's equivalence principle, suggests that the immense gravitational gradient at the horizon should produce an effect analogous to the Unruh effect. An observer hovering just outside the horizon, firing their rockets desperately to avoid falling in, would perceive the quantum vacuum as a thermal state. They would see the Hawking radiation. But an astronaut in freefall crossing the horizon smoothly would see nothing of the sort. For them, the vacuum remains a vacuum. This stark difference in perception underscores a profound question. What is the true, objective nature of the vacuum near a black hole? Is it teeming with radiation, or is it empty? The answer seems to be that both perspectives are correct for their respective observers, a paradox that lies at the heart of the conflict between quantum theory and gravity. This intense quantum activity suggests that the event horizon might not be the perfectly smooth boundary we imagine. The constant creation and annihilation of virtual particles, the very process that gives rise to Hawking radiation, might churn the spacetime at the horizon into a roiling, chaotic foam. At the tiniest conceivable scales, at the Planck length, the fabric of spacetime itself may be subject to wild quantum fluctuations. The smooth, classical geometry described by Einstein's equations might break down, replaced by a turbulent, foamy structure where causality and locality become ill-defined concepts. In this view, the horizon is not a sharp line but a blurry, dynamic interface. It might be more accurate to think of it as a quantum transition zone rather than a precise boundary. This fuzziness could have dramatic consequences. It might provide a mechanism for information to leak out of the black hole, scrambled into the Hawking radiation. It could also mean that the notion of falling through the horizon is not the clear-cut event of classical physics, but a gradual process of becoming entangled with the quantum state of the black hole itself. The smooth event horizon of general relativity may be an idealization, a macroscopic average that masks a microscopic reality of unimaginable complexity and chaos. Considering the cosmic monsters we have already encountered, from stellar mass remnants to the supermassive giants anchoring galaxies, it is natural to wonder if there is any ceiling to their growth. Is there a point where a black hole simply cannot get any bigger, a fundamental limit imposed by the architecture of the universe itself? This question leads us to a truly grand-scale mystery, the maximum possible size of a black hole. In a static, infinite universe, the answer might seem straightforward. They could, in theory, continue to consume stars, gas, and even other black holes forever, growing without bound. But our universe is not static. It is expanding, and that expansion is accelerating due to the mysterious influence of dark energy. This cosmic acceleration places a profound constraint on the ultimate fate and size of these gravitational behemoths. The key to understanding this limit lies in the concept of a cosmological horizon, which is distinct from a black hole's event horizon. Our observable universe has a finite size, a boundary defined by the distance light has had time to travel since the Big Bang, about 46 billion light-years in every direction. This is our cosmic bubble, our Hubble volume. Outside of this sphere, galaxies are receding from us faster than the speed of light due to the expansion of space itself, meaning their light can never reach us and we can never interact with them. Now imagine a supermassive black hole at the center of a galaxy, voraciously accreting matter. As it grows, the radius of its event horizon expands. But the black hole is sitting within an expanding cosmos. For it to continue growing, it must pull in matter from its surroundings. However, as dark energy causes the expansion to accelerate, the distance between galaxies increases and the density of matter in the universe drops. Eventually, a point will be reached where the space around the black hole is expanding away from it faster than the black hole's gravity can pull matter inward. Think of it as a spider on a stretching rubber sheet. The spider can pull in insects that are close by, but if the sheet is being stretched rapidly, insects that are too far away will be pulled away faster than the spider can reel them in. For a black hole, this creates a de facto feeding zone, a region of gravitational influence beyond which all matter is forever out of reach. The size of this zone is determined by the balance between the black hole's gravity and the expansion rate of the universe, known as the Hubble constant. A black hole can only accrete matter that lies within its cosmic sphere of influence. Once it has consumed everything within that sphere, its growth stops. This suggests a theoretical maximum mass, which some calculations place at around 100 billion times the mass of our Sun, a scale truly befitting the largest structures in the cosmos. There are already candidate black holes like the one at the heart of the galaxy home 15A that are estimated to be tens of billions of solar masses pushing against this theoretical boundary. But this leads to an even more mind-bending hypothetical, a thought experiment that pushes the limits of cosmology itself. What would happen if a black hole's event horizon were to grow so vast that it approached the size of the observable universe? This is not a scenario that can happen in our universe's future, given the dominance of dark energy, but it is a profound theoretical puzzle. If such a black hole existed, its event horizon and our cosmological horizon would begin to coincide. The point of no return for the black hole would become the point of no return for the entire observable cosmos. In such a state, the distinction between being inside a black hole and simply living in the universe would blur into meaninglessness. Some cosmologists like Nikodem Poplawski have taken this idea even further, proposing that our entire universe could exist within a black hole residing in a parent universe. In this cosmological natural selection model, the Big Bang was the white hole explosion from a black hole collapse in another cosmos. If this is true, then we are already living inside the ultimate black hole, and the observable universe is simply its interior. This idea provides a potential explanation for why our universe appears to have such finely tuned constants. Those that produced successful black holes in a parent universe would be the ones to spawn new universes, creating an evolutionary pressure for universes that are good at making black holes. While this is highly speculative, it forces us to confront the deep connections between the physics of the incredibly small and the cosmology of the incredibly large. The ultimate size limit of a black hole is not just a question about a single object. It is a question about the global geometry and fate of the entire cosmos. It ties the destiny of the largest gravitational structures directly to the nature of dark energy. If the acceleration continues indefinitely, leading to a Big Rip scenario, then all black holes will eventually be isolated and starved, their maximum size capped by the conditions of the early universe. If the nature of dark energy changes, perhaps reversing the acceleration, then a different, even more dramatic future for black hole growth could be possible. The mystery of their maximum size is therefore a window into the ultimate fate of everything, a reminder that the laws governing the smallest quantum flicker are inextricably linked to the destiny of the entire universe. Yet as we contemplate the ultimate limits of size and containment, we are drawn to a mystery that touches the very flow of reality itself, the nature of time. Our daily experience tells us time has a direction, an arrow that flies relentlessly from the past through the present and into the future. We remember yesterday but not tomorrow. A cup shatters on the floor, but the pieces never spontaneously reassemble. This one-way street is so fundamental to our existence that we rarely question it. Yet, the fundamental laws of physics, from Newton's mechanics to Einstein's relativity and even quantum theory, are almost entirely time-symmetric. The equations work just as well if time runs backward. So where does time's arrow come from? The answer, surprisingly, may be written in the gravitational collapse of black holes and is deeply connected to the concept of entropy we explored earlier. To understand this, we must revisit the second law of thermodynamics, which states that the total entropy of a closed system always increases. Entropy is a measure of disorder, and the law tells us that the universe as a whole is progressing from a state of order to a state of disorder. This relentless increase in disorder is what gives us the arrow of time. The reason you can tell if a video of a splashing water droplet is playing forward or backward is because the forward direction is the one where the entropy increases. Now, black holes enter this picture in a dramatic way through their immense entropy. Jacob Bekenstein and Stephen Hawking discovered that a black hole's entropy is colossal, proportional to the area of its event horizon. This means that when a single gram of matter falls into a black hole, the increase in the black hole's entropy is staggeringly larger than the entropy that gram of matter possessed in any other form. A black hole is the universe's ultimate entropy engine. It is the most efficient and powerful method for increasing disorder ever conceived. This fact ties the arrow of time directly to gravity. For most of the universe's history, the increase in entropy was a relatively gentle process, driven by things like heat diffusion and chemical reactions. But the formation of black holes represents a quantum leap in the universe's disorder. When a massive star collapses or when two galaxies merge their central black holes, there is a sudden, catastrophic increase in entropy on a scale that dwarfs all other processes. The gravitational pull of a black hole acts as a cosmic amplifier for the second law of thermodynamics. The arrow of time, therefore, may not be a gentle, universal breeze, but rather a river whose current is dramatically stiffened by the gravitational waterfalls of black holes. Their formation and growth are major events that punctuate the timeline of the cosmos, driving the overall increase in disorder that defines the forward direction of time. This leads to one of the most profound puzzles in all of science. Why did the universe start with such incredibly low entropy? The Big Bang appears to have been a state of exquisite order, a smooth, hot, dense soup with very little initial disorder. This low entropy starting point is the ultimate source of the arrow of time. It's the wound-up spring that has been unwinding for 13.8 billion years. But why was the spring wound up in the first place? What set the cosmic clock ticking from such an ordered beginning? Black holes, and particularly their evaporation, might hold a clue to this deepest of mysteries. The process of Hawking radiation, which causes black holes to slowly lose mass and eventually evaporate, is irreversible. It is a one-way street. The information that was seemingly lost inside is, according to most modern theories, scrambled and returned to the universe in the radiation, but the black hole itself is gone forever. This irreversible loss of a gravitational structure could be a key part of the universe's long-term evolution toward a maximum state of entropy, a featureless heat death. Some physicists like Sean Carroll have proposed that the low-entropy Big Bang might not be a unique starting point. Instead, it could be just one phase in a much larger multiverse. In this view, the arrow of time might not be an absolute property of the cosmos, but a local phenomenon. Our universe is a fluctuation away from equilibrium, a temporary bubble of order within an eternally chaotic multiverse. Within our bubble, the formation of black holes and their eventual evaporation are the dominant processes that define the direction of time's arrow for us. As the universe continues to expand and cool, black holes will be the last great structures, slowly leaking their energy away until even they are gone. The final state of the universe would be a cold, dark, empty void at maximum entropy, a state with no structure and no arrows of time. In such a state, the concepts of past and future would become meaningless. The existence of black holes, therefore, might be the very mechanism that creates a clear, irreversible timeline within our cosmic epoch, a temporary island of causality in an eternal sea of randomness. They are not just objects within time, they may be the architects of time's flow as we experience it. But of all the cosmic collisions now being heard through gravitational waves, perhaps the most enigmatic are those that involve fundamentally different kinds of monsters. We have explored the mergers of black holes with black holes, but what happens when a black hole meets a neutron star? This is a clash of titans unlike any other, a confrontation between the ultimate vacuum cleaner and the ultimate pressure cooker. A neutron star is the super-dense, city-sized remnant of a supernova, a ball of matter so compressed that a single teaspoon of it would weigh billions of tons. It is matter pushed to the very brink of becoming a black hole, but held up by a fierce quantum mechanical pressure known as neutron degeneracy. When a black hole enters the picture, it poses a direct, violent challenge to that pressure. The mysteries of these collisions, now being detected by observatories like LIGO and Virgo, are giving us a front-row seat to the most extreme physics experiment in the universe, probing the nature of matter itself. The central drama of such an event is a question of annihilation versus resistance. What happens when the inescapable gravity of the black hole meets the nearly indestructible density of the neutron star? There are two primary dramatic scenarios, and the outcome hinges on a delicate balance of masses and distances. If the black hole is significantly more massive than the neutron star, the encounter is likely brief and brutal. The black hole's immense tidal forces, the difference in gravity between the near and far sides of the neutron star, would overwhelm the internal forces holding the star together long before the two objects make contact. In this case, the neutron star would be shredded in a spectacular tidal disruption event. It would not be swallowed whole. Instead, it would be stretched and torn apart into a long, thin stream of ultra-dense matter, forming a searingly hot accretion disk around the black hole before being gradually consumed. This process would release a tremendous burst of energy across the electromagnetic spectrum, from gamma rays to visible light. It would be a fleeting cosmic firework, a brilliant flash signaling the death of a star that dared to venture too close. However, if the black hole is of a lower mass, or if it is slowly spinning, the story could be different. The tidal forces might be weaker, and the neutron star's incredible density might allow it to hold together longer, potentially surviving right up to the moment of merger. In this scenario, the two objects could spiral together and collide more directly. The fate of the neutron star in this instant is one of the greatest unknowns. Does it simply plunge into the black hole, vanishing without an electromagnetic trace, much like a black hole merger? Or does its immense density and strange internal structure cause a more complex and observable reaction? The answer depends on the very property we are trying to measure, the equation of state of ultra-dense matter. This equation of state is essentially a rulebook that describes how matter behaves under pressures and densities so extreme they cannot be replicated in any laboratory on Earth. It tells us how squishy or stiff a neutron star is. A softer, more compressible star would be more easily pulled apart by tidal forces, while a stiffer, more rigid star could resist disruption until the very last moment. This is why these collisions are such a scientific goldmine. The gravitational wave signal from such an event is exquisitely sensitive to the properties of the objects involved. As the black hole and neutron star spiral inward, their gravitational waves carry an imprint of their masses and, crucially, their tidal deformability. Just as the moon's gravity stretches the Earth's oceans to create tides, the black hole's gravity stretches the neutron star. A squishy star will deform more easily, creating a larger tidal bulge, which in turn affects the gravitational wave signal in a detectable way during the final orbits before merger. By carefully analyzing the chirp of the waves, scientists can extract information about the neutron star's size and its equation of state. A detection of a bright electromagnetic counterpart, a flash of light, alongside the gravitational waves would be the smoking gun, confirming that the neutron star was torn apart and that its debris produced a fiery aftermath. The absence of such a flash would suggest a more direct, silent plunge. The first confirmed detection of a black hole neutron star merger, announced in 2021, provided a tantalizing but ambiguous glimpse. The events, detected just days apart, involved a black hole about 6 times the mass of the Sun consuming a neutron star. Intriguingly, no accompanying flash of light was found. This could mean that in these cases, the neutron stars were swallowed whole, or that any disruption happened too quickly or in too isolated a region to produce an observable signal. Each new detection adds a crucial data point, helping us to map out the conditions that lead to a tidal disruption versus a direct plunge. These events are not just cataclysmic endings, they are cosmic crucibles. The moment of collision creates conditions of temperature and density that are more extreme than anything since the first microseconds after the Big Bang. It is within this maelstrom that we might finally answer profound questions about the nature of neutron star material. Could it undergo a phase transition into a soup of free quarks, creating a strange matter star? Does it form exotic states like hyperons or pion condensates? The collision is a fleeting, natural laboratory that takes the mystery of what lies at the heart of a neutron star and smashes it against the ultimate abyss, giving us a unique opportunity to decode the laws of physics at their absolute limit. While the serene, non-rotating black hole provides a tidy introduction, the universe's real black holes are far from static. Almost every black hole we have observed spins, some at a significant fraction of the speed of light. This rotation complicates the picture immensely, transforming the simple Schwarzschild solution into a dynamic, whirling vortex described by a more complex set of equations known as the Kerr metric. Discovered by New Zealand mathematician Roy Kerr in 1963, this solution describes a black hole that not only has mass but also angular momentum. The geometry around a spinning black hole is radically different. Instead of a simple spherical event horizon, the black hole develops a region of space just outside the horizon called the ergosphere, where the dragging of spacetime is so powerful that nothing can remain stationary. It's a cosmic whirlpool where space itself is forced to rotate with the black hole. Within the ergosphere, you would be compelled to move, a prisoner of the black hole's rotation. The singularity at the center is no longer a point but is smeared into a ring, a one-dimensional loop. This ring singularity is so bizarre that, in theory, it could act as a gateway to other universes or other points in time, though actually traversing it would likely be fatal. The Kerr metric is a beautiful and vital solution, as it describes the realistic astrophysical black holes we actually see. For decades, it has been considered a stable solution within the pure framework of general relativity, meaning small perturbations should settle down, not grow uncontrollably. But this perceived stability rests on a classical foundation, and when we introduce the quantum world or ideas from string theory, the picture becomes far less certain. The central mystery here is whether the Kerr black hole remains stable when we go beyond Einstein's theory. This is not an abstract mathematical worry. It strikes at the heart of whether our descriptions of these objects are truly complete. The primary mechanism for potential instability is a fascinating and powerful phenomenon called superradiance. Imagine sending a wave, it could be a light wave, a gravitational wave, or even a matter wave, toward a rotating black hole. If the wave has a frequency lower than the rotation rate of the black hole, a remarkable thing can happen. Instead of being swallowed, the wave can extract rotational energy from the black hole itself and bounce away with more energy than it arrived with. It is akin to a tennis ball hitting a moving paddle. If the ball hits at the right angle, it comes back faster. In this case, the black hole's spin is the paddle. The wave steals a tiny bit of the black hole's rotational energy and is amplified as it escapes. This is not science fiction. It is a direct prediction of general relativity. Now consider what might happen if this amplified wave, instead of escaping to infinity, becomes trapped. If there is a natural mirror around the black hole, such as a surrounding cloud of plasma, or even the effective potential barrier created by the black hole's own gravity, the wave could reflect back toward the black hole. It would then be amplified again by superradiance, reflect off the mirror, and return even stronger. This creates a runaway feedback loop, a phenomenon known as a black hole bomb. The energy in the trapped wave would grow exponentially, extracting more and more spin from the black hole until the instability either dissipates the rotation or disrupts the system entirely. In a pure vacuum, this doesn't happen for electromagnetic or gravitational waves as they escape easily. but for more exotic fields, such as those predicted by theories beyond the standard model, the story could be different. This is where the stability of the Kerr metric faces its greatest test. When we incorporate quantum field theory, the vacuum around the black hole is not empty but filled with virtual particles. Superradiants can act on these quantum fields. A rotating black hole could spontaneously create pairs of particles from the quantum vacuum, with one particle carrying negative energy falling in and reducing the black hole's spin, while its partner, amplified by superradiance, escapes as a real particle. This is a quantum version of the superradiant process. The question is whether this quantum stimulation could lead to large-scale instabilities that would fundamentally alter the black hole or reveal new physics. Furthermore, in theories that propose extra dimensions of space, such as string theory, there could exist a whole spectrum of new ultra-light particles. For a rotating black hole, these particles could be efficiently produced via superradiance, forming a dense, gravitationally bound cloud around it. This cloud would act as its own mirror, trapping the waves and leading to a continuous drain on the black hole's rotational energy. The black hole would literally be shrouded in a bosonic cloud of its own making, a visible signature of new physics. The ongoing search for gravitational waves from black holes includes looking for the faint, persistent hum that such a cloud would produce, a direct test of the Kerr metric stability against quantum and extra-dimensional effects. The stability of the rotating black hole is therefore a critical benchmark. If the Kerr solution is found to be unstable under these more complete physical theories, it would mean that realistic black holes may not settle into the simple, clean states we have long assumed. They might instead pulsate, shed rotating clouds of exotic particles, or even transition into new types of objects entirely. Proving its stability, on the other hand, would be a powerful vindication of general relativity, even in the face of quantum corrections. It would show that Einstein's theory, for all its known limitations, provides an incredibly robust description of these cosmic engines. The mystery hinges on observations, on listening for the telltale signs of superradiant clouds with gravitational wave detectors, and watching for the unique energy signatures they would emit. The silent spin of a black hole may be hiding a vibrational storm, an instability that only a deeper union of gravity and quantum mechanics can reveal. Yet as we consider the bizarre quantum fuzz and the potential for superradiant instabilities around a spinning black hole, we are led to a possibility that is perhaps the most profound synthesis of all: the idea that a black hole might not just be a gravitational object but a cosmic computer. This is not a metaphor. The laws of physics tell us that information cannot be destroyed, and the holographic principle suggests that all the information about what fell into a black hole is encoded on its two-dimensional event horizon. If that is true, then the black hole must be processing that information. It must be performing a computation of unimaginable complexity and speed. The black hole, in this view, becomes the universe's ultimate quantum computer, and understanding its operation could unlock the deepest secrets of reality itself. To grasp this, we need to think about what happens to information when it falls into a black hole. From our perspective outside the information, the unique quantum states of every atom and particle seems to vanish. But the holographic principle asserts it is not lost. It is instantly transferred to the surface of the event horizon. However, it doesn't appear there in an orderly fashion like a book on a shelf. Instead, it is scrambled. It is thrown into a state of such extreme chaos that every piece of information becomes inextricably mixed with every other piece. If you could read the horizon, it would look like pure, random noise. This process is known as quantum scrambling, and it is something that all complex quantum systems do. But a black hole doesn't just scramble information. It does it with a speed and efficiency that is utterly staggering, a phenomenon physicists call fast scrambling. Imagine throwing a deck of cards into the air. In a normal system, it might take a while for the order of the deck to become completely randomized as the cards interact with each other and the air. But in a fast scrambler, the randomization is almost instantaneous. For a black hole, the scrambling time, the time it takes for any information to become thoroughly mixed across the entire system, is proportional to the logarithm of the number of bits of information stored on the horizon. This is exponentially faster than any other known physical process. An ordinary hot gas of particles scrambles information in a time proportional to the number of particles. A black hole does it in a time proportional to the logarithm of that number. This is a difference of kind, not just degree. It means that a black hole is the most efficient information processor in the known universe. It is performing a computation that would take any system we could build an astronomically longer time to complete. This has led to a breathtaking proposal. The black hole is not just a fast scrambler by accident. It is, in fact, achieving the fundamental physical limit for how quickly information can be processed. This is the ultimate speed limit of computation, set not by engineering constraints, but by the laws of quantum mechanics and gravity. If this is true, then studying black holes is not just about astrophysics. It is a direct probe into the fundamental limits of information processing in our universe. It suggests that space, time, and gravity might themselves be emergent properties of a vast, underlying quantum computation happening at the Planck scale. In this it-from-bit worldview, the universe isn't just described by information, it is information. The three-dimensional reality we experience is a projection, an output of a cosmic quantum computation, and black holes are the regions where this computational nature is laid bare, where the hardware of reality is pushed to its absolute limits. What would this cosmic computer be calculating? One compelling, though highly speculative, idea is that it is running the simulation of its own interior. The holographic principle suggests the three-dimensional volume inside the black hole is an illusion, a projection from the data on the two-dimensional surface. In this view, the black hole's computation is the act of translating the scrambled data on the horizon into the internal experience of spacetime, gravity, and the infalling matter. It is literally computing the reality of its own interior. This raises a dizzying possibility. If our universe is holographic, then our entire cosmos could be the result of a similar computation running on the boundary of our observable universe. The laws of physics we discover would then be the algorithms of this grand computation. This connection makes black holes a unique laboratory for a field known as quantum gravity, which seeks to unify general relativity with quantum mechanics. Physicists are now building tabletop experiments to simulate the conditions of a black hole's event horizon using ultra-cold atoms, lasers, and even superconductors. These are not literal black holes, but carefully controlled quantum systems that are designed to behave according to the same mathematical principles. By studying how information scrambles in these lab-grown black holes, scientists hope to witness signatures of fast scrambling and perhaps even glimpse how spacetime itself emerges from quantum entanglement. A detection of fast scrambling in such an experiment would be a monumental step, providing tangible evidence that the same fundamental informational processes are at work in both a crystal-cooled quantum circuit and the fiery maw of a galactic giant. The black hole, therefore, transcends its role as a cosmic monster. It becomes a teacher, a Rosetta Stone for translating the language of gravity into the language of quantum information, offering us a chance to read the source code of the universe itself. Yet for all the power locked in a black hole's spin and gravity, there is a third, invisible force that plays an equally critical role in shaping its most dramatic outbursts: magnetism. We've seen how jets are launched and focused by magnetic fields, but this begs a deeper question. Where do these incredibly powerful fields originally come from? A black hole itself, defined only by its mass, spin, and charge, possesses no intrinsic magnetic field. The source of this cosmic power lies in the frenetic chaos of its accretion disk, in a complex dance of ionized gas and fundamental physics known as magnetohydrodynamics. The mystery is not just about the existence of these fields, but about the specific, highly efficient dynamo processes that can amplify a faint, seed magnetic field into a structured powerhouse capable of reigning over the black hole's immense gravity. The story begins with the fuel itself, the accretion disk. This is not a simple, placid whirlpool of gas. It is a superheated, turbulent plasma, a sea of charged particles spiraling inward. Crucially, within this plasma, even the weakest magnetic field lines are frozen into the gas, a principle known as Alfvén's theorem. As the disk rotates, it drags these magnetic field lines along with it. Now, imagine stretching a strand of spaghetti. The differential rotation of the disk, where inner regions orbit much faster than outer regions, winds up these magnetic field lines, stretching them and winding them around the black hole like thread on a spool. This winding process transfers the rotational energy of the disk directly into the magnetic field, amplifying its strength tremendously. But this is only the first step. The real magic, the true dynamo, requires turbulence. A perfectly smooth, orderly disk would not generate a sustained field. It is the chaotic, churning motion within the plasma that creates the dynamo effect. Small-scale turbulent eddies twist and fold the magnetic field lines, a process that can regenerate a magnetic field if it begins to decay, and under the right conditions, amplify it exponentially. This is analogous to the dynamo that powers Earth's magnetic field, where the convection of molten metal in the core generates our planetary magnetosphere. But around a black hole, the scales and energies are almost incomprehensibly larger. The key is the magnetorotational instability, or MRI. This is a beautiful and powerful instability that explains why accretion disks are inherently turbulent. In a disk where gas is supported against gravity by rotation, a weak magnetic field creates a fragile coupling between adjacent layers. A parcel of gas orbiting slightly farther out moves a little slower than a parcel slightly closer in. The magnetic field linking them acts like a spring. The inner, faster parcel pulls forward on the outer, slower one, transferring angular momentum outward. This allows the inner parcel to fall even further inward, gaining speed, while the outer parcel is pushed further out. The result is a runaway process that churns the entire disk into a state of intense turbulence, which in turn drives the magnetic dynamo to incredible efficiencies. Supercomputer simulations are our primary window into this invisible struggle. Researchers create virtual black holes surrounded by millions of particles representing the plasma, and then apply the laws of magnetohydrodynamics to watch the system evolve. These simulations are computationally monstrous, but they reveal the breathtaking emergence of order from chaos. They show how the turbulent dynamo can indeed amplify fields to strengths where they become dominant forces, capable of launching jets. They also reveal a fascinating self-organization. The magnetic fields don't just become a uniform fog. They often organize into large-scale, ordered structures, like a gigantic dipole field aligned with the black hole's spin axis, which is exactly the configuration needed to create the narrow, focused jets we observe. Yet, these simulations also highlight the gaps in our understanding. The final strength and precise geometry of the field seem to depend sensitively on initial conditions we cannot directly observe, such as the exact amount and configuration of the seed magnetic field that was present in the gas long before it ever reached the black hole. This is where cutting-edge observations, particularly from the Event Horizon Telescope, are providing real-world data to test the simulations. The EHT's images of the black hole in Messier 87 are not just pictures of a shadow, they are also maps of polarized light. Polarization tells us the orientation of the magnetic fields in the hot plasma swirling near the event horizon. The results were striking. They showed a powerful, well-organized magnetic field with a significant portion of its energy in a large-scale spiral pattern. This is a direct observational confirmation that the dynamo process is not just theoretical, it is happening, and it is creating the structured fields needed to power the jet. However, the observations also showed that the field is incredibly tangled and complex close to the black hole, a sign of the intense turbulence predicted by the MRI. The great challenge now is to unify the simulation data with the observational data to understand the complete life cycle of these fields, from their origin as faint seeds in intergalactic space, through their amplification in the turbulent disk, to their final organization into the universe's most powerful particle accelerators. Solving this magneto-hydrodynamic mystery is essential because it is the final piece in understanding how a black hole, an object of ultimate darkness, can become a beacon of light. But beyond the magnetic dynamo and the violent jet-launching mechanisms, there is a zone of even more concentrated fury, a place where matter makes its final, frenzied orbits before the ultimate plunge. This is the inner accretion disk, a region so close to the event horizon that the laws of physics are stretched to their absolute breaking point. Imagine a cosmic carousel spinning at a significant fraction of the speed of light, a whirlpool of superheated plasma where temperatures soar to billions of degrees and the very fabric of space and time is whipped into a vortex by the black hole's spin. It is here, in this last frenetic dance before the abyss, that some of the most intriguing and puzzling signals from black holes are born. One of the most fundamental mysteries of this region is a seeming paradox. How does the gas in the accretion disk actually lose energy to spiral inward? In the vacuum of space, there is no physical friction like air resistance to slow the orbiting material down. Each particle is essentially in a perpetual free-fall orbit, governed by gravity alone. For it to spiral down, it must somehow shed orbital energy and angular momentum. The answer lies not in simple friction, but in a complex and beautiful instability we touched upon earlier, the magnetorotational instability, or MRI. While the magnetic dynamo amplifies the field, the MRI is the engine of transport. It works by exploiting a simple fact. In a disk of gas, material closer to the black hole orbits faster than material further out. A weak magnetic field connecting these two regions acts like a spring. The faster inner gas pulls forward on the slower outer gas, speeding it up and pushing it further outward. Conversely, the outer gas pulls backward on the inner gas, slowing it down and causing it to fall to a lower orbit. This transfer of angular momentum outward allows the inner material to lose energy and spiral inexorably inward, all driven by the magnetic coupling. It is an incredibly efficient process, turning the entire disk into a turbulent, energy-dissipating machine that allows the black hole to feed. As this plasma churns and heats to incredible temperatures in the inner disk, it emits a torrent of high-energy radiation, primarily in the form of X-rays. By pointing X-ray telescopes at black holes, we can watch this light flicker and flare, but it doesn't just flicker randomly. Astronomers have detected a fascinating phenomenon known as quasi-periodic oscillations, or QPOS. These are rhythmic, nearly periodic flickers in the X-ray brightness, like a cosmic heartbeat. They are not perfectly regular clocks. Their frequency drifts and changes, which is why they are called quasi-periodic. But their presence is a tantalizing clue. The prevailing theory is that these QPOS are caused by hotspots or blobs of plasma orbiting in the very inner edge of the accretion disk. As these blobs whip around at near light speeds, their X-ray emission is boosted and dimmed by the extreme Doppler effect and gravitational lensing, creating a rhythmic signal as they pass in and out of our view. The frequency of this signal is directly tied to the orbital period at that specific radius. This is where these oscillations become a powerful tool for fundamental physics. The orbital period of matter just outside a black hole depends only on the black hole's mass and spin, and the severe warping of spacetime described by general relativity. By measuring the frequency of a QPO, we can effectively measure the orbital speed at the innermost stable circular orbit, a critical boundary predicted by Einstein's theory. This allows us to not just weigh the black hole, but to estimate how fast it is spinning. It's like being able to listen to the hum of a spinning top and deduce both its weight and its rotational speed. Different QPO frequencies are thought to correspond to different vibrational modes of the inner disket's radial oscillations, vertical oscillations, and precession, all of which are orchestrated by the black hole's gravity. By deciphering this complex symphony of X-rays, we are conducting remote experiments in strong field gravity, testing whether Einstein's predictions hold up in the most extreme environment imaginable. Each flicker is a data point from the edge of spacetime, a direct probe of gravity when it is no longer a gentle force but a dominant, twisting curvature that dictates the motion of light and matter alike. But if the interior of a black hole can be a bridge, and if our universe itself might be the product of a singularity, we are led to one of the most breathtaking frontiers of all: the possibility that black holes are not merely objects within our cosmos, but are literal connections to a vast multiverse. This idea pushes speculative cosmology to its absolute limit, suggesting that these gravitational abysses could be cosmic wormholes, stitching together the fabric of separate realities. The mathematics of general relativity does not forbid such a connection. In fact, the simplest black hole solution, when extended, naturally includes a tunnel, an Einstein-Rosen bridge, that leads to a different spacetime region. In this purely mathematical view, falling into a black hole wouldn't end at a singularity, but would instead transition you through a throat, emerging from a white hole into another universe entirely. It's a concept that transforms black holes from ultimate endpoints into potential gateways, making them the linchpins in a cosmos of cosmoses. This notion finds a more concrete form in the theory of cosmological natural selection, a provocative idea proposed by physicist Lee Smolin. He suggested that what we call the Big Bang could actually have been the formation of a white hole, the explosive other end of a black hole collapse that occurred in a parent universe. In this scenario, every black hole in our universe could be giving birth to a new, budding universe of its own, with its fundamental constants and physical laws slightly tweaked or mutated during the process. This creates a form of cosmic Darwinism. Universes that produce more black holes will have more offspring, leading to a multiverse naturally selected for the conditions that favor black hole formation. It's a staggering cycle of death and rebirth on a scale beyond comprehension, where our entire reality is just one branch on an infinite fractal tree of universes, and the supermassive black holes at galactic centers are not monsters but the seeds of future cosmic generations. A related but distinct vision comes from string theory, which posits that our universe is a three-dimensional membrane, or brain, floating in a higher dimensional space. In this brain world scenario, a black hole in our universe might not puncture a hole to another dimension within our own spacetime, but could instead be a gravitational funnel that connects our brain to another one floating parallel to us. The event horizon would be the point where matter is transferred from one membrane to another, effectively teleporting it to a separate reality with potentially different physical laws. This provides a potential, though highly theoretical, resolution to the information paradox. The information isn't destroyed, it's merely ejected into a universe that is causally disconnected from our own. While this sounds like the plot of a science fiction novel, it emerges from serious attempts to reconcile gravity with quantum mechanics in a framework that requires extra dimensions. The monumental challenge, of course, is testing any of this. How can we possibly gather evidence for a reality that exists beyond our causal horizon? The answer may lie not in direct observation, but in searching for faint, indirect fingerprints left on our own universe. If our universe was indeed born from a black hole in a parent cosmos, that violent genesis might have imprinted a specific signature on the cosmic microwave background radiation, the afterglow of our own Big Bang. Certain anomalous patterns or asymmetries in this background haze could, in theory, be the scars of that primordial event. Similarly, if black holes are truly gateways, the process of information transfer or the specific spectrum of Hawking radiation they emit in their final moments might carry a subtle code, a signature of the new physics governing the connection to another reality. The detection of a primordial gravitational wave background, a relic from the universe's first instance, could also reveal details about the initial conditions that would support or refute the black hole genesis idea. Ultimately, the multiverse hypothesis remains one of the most controversial ideas in modern science precisely because it currently resides at the edge of testability. For some, it is a necessary consequence of theories like inflation and string theory. For others, it is an untestable metaphysical speculation. Yet, the connection to black holes gives it a tangible, physical anchor. These objects are real, their interiors are governed by laws we do not understand, and their properties challenge the foundations of physics. Whether they are revealed to be dead ends, gateways, or cosmic wombs, their true nature will undoubtedly force us to radically reconsider our place in reality. They are the ultimate mystery boxes of the cosmos, and opening them might not just reveal what's inside, but could show us that inside is a far more expansive and bewildering concept than we ever dared to imagine. But if the event horizon is a firewall and the interior a potential gateway, we must now follow the black hole's own life cycle to its ultimate conclusion. We've seen how Hawking radiation slowly steals a black hole's mass, causing it to shrink over trillions of years. But this evaporation is not a gentle fading. It is a process that accelerates dramatically as the black hole becomes smaller and hotter. This leads us to a mystery that pits the graceful exit predicted by quantum mechanics against the violent end demanded by general relativity. What is the final state of an evaporating black hole? When the last bit of mass is gone, what remains? The answer is not just about the death of a single object. It is the final chapter of the information paradox, a moment where the universe must make a choice about its most fundamental rules. The classical and seemingly simplest answer is that the black hole vanishes completely. In this scenario, the evaporation continues unimpeded. As the black hole shrinks, its temperature rises, causing it to radiate energy away faster and faster. The final moments would be a runaway explosion, a tremendous burst of high-energy particles and radiation as the last vestiges of mass are converted into Hawking radiation. Then silence. The black hole would simply cease to exist, leaving behind only a faint, expanding cloud of thermal radiation. This is a clean, decisive end. But it is also a catastrophic one for the principle of quantum unitarity, which dictates that information cannot be lost. If the black hole vanishes entirely, then all the information about every star, planet, or book that ever fell into it vanishes with it, scrambled into a featureless bath of random heat. This complete disappearance is the ultimate violation, a cosmic deletion of information that would force us to rewrite quantum mechanics itself. It is the final victory for Hawking's original, alarming conclusion. To avoid this information apocalypse, physicists have proposed a more subtle finale. Perhaps the black hole does not evaporate completely. Instead, as it approaches the microscopic scale of the Planck length, the realm where quantum gravity must take over, the evaporation process could halt. What remains is a stable, indestructible relic, a particle with a mass roughly equal to the Planck mass, a minuscule 20 micrograms but astronomically dense. This Planck mass relic would be a frozen fragment of the original black hole, a tiny vault containing all the information that ever fell in. It would be immune to further decay because any attempt to probe it or break it apart would require energies so high that they would themselves create a new black hole, effectively protecting the relic from being dismantled. In this scenario, information is preserved not by being radiated away, but by being locked away forever in a permanent, inaccessible tomb. The universe's ledger remains balanced, but the information is sentenced to eternal imprisonment, forever hidden from view. A third, even more exotic possibility is that the evaporation process itself undergoes a radical transformation at the quantum gravity scale. Rather than exploding or leaving a relic, the black hole's interior geometry could undergo a quantum bounce. Imagine the collapse in reverse. As Hawking radiation reduces the mass to a critical threshold, the extreme quantum pressures at the core become repulsive instead of attractive. The singularity would rebound and the event horizon would vanish. In a flash, the black hole would transform into a white hole, violently ejecting all its remaining mass and energy, and with it, the stored information back into the universe. This would be a spectacular death, a final act of cosmic rebirth where the black hole turns itself inside out. The information isn't slowly leaked or locked away, it is returned in a sudden, fiery eruption. This provides an elegant, if dramatic, solution to the information paradox, but it requires that white holes, which we have never observed, are a genuine feature of quantum gravity. The choice between these fates, complete evaporation, a stable relic, or a quantum bounce, is not merely academic. It is a direct test of how the laws of quantum gravity behave under the most extreme conditions. The final microseconds of a black hole's life would be a maelstrom of quantum gravitational effects, a domain where our current theories are mere guesses. Observing such an event, should a primordial mini black hole be found and its death throes monitored, would provide an unparalleled window into this unknown physics. The specific spectrum of particles emitted in the final burst would be the ultimate clue. If the radiation is purely thermal until the very end, it suggests information loss. If there are subtle deviations from a perfect thermal spectrum, complex correlations between the early and late radiation, it would be the smoking gun that information is being encoded and returned. The death of a black hole is therefore its most eloquent statement, a final message that reveals whether the universe truly forgets or if it never, ever lets anything go. Now we venture into a mystery that is all about motion, a hidden property that transforms a simple black hole into a cosmic vortex, spin. While we often picture these objects as static pits, the reality is that nearly every black hole we've detected is rotating, some at velocities that defy imagination, approaching the ultimate speed limit set by light itself. Yet curiously, not all black holes are spinning rapidly. Some are relative sluggards. This variation presents a fascinating puzzle. What determines how fast a black hole twirls? The answer is a cosmic story written in the history of its birth, its diet, and its most violent collisions. To understand why spin matters, we have to go beyond the simple Schwarzschild black hole. A rotating black hole, described by the Kerr solution, is a far more dynamic and complex beast. Its rotation drags the very fabric of spacetime around with it, a phenomenon known as frame dragging, creating a region just outside the event horizon called the ergosphere. Within this zone, nothing can remain stationary. Everything is compelled to move with the whirling spacetime. This rotational energy isn't just for show. It's a vast reservoir of power. In fact, a spinning black hole stores tremendous energy in its rotation, energy that can, in theory, be extracted. This is the mechanism behind the universe's most powerful engines, like the relativistic jets that scream from active galactic nuclei. The spin is the battery that makes it all possible. So, how does a black hole get its spin in the first place? It all comes down to angular momentum, the same principle that makes a figure skater spin faster when they pull their arms in. When a massive star reaches the end of its life and its core collapses, it holds onto the angular momentum of the original star. Imagine that star was rotating, even slowly. As the core implodes from a size millions of kilometers across down to a mere few dozen kilometers, The conservation of angular momentum demands that its rotation rate skyrocket, just like that skater. This is the birth spin, the initial kick that every stellar mass black hole receives. But this is just the beginning of the story. The black hole's spin can be dramatically altered afterward by what it consumes. This is where the process of accretion comes into play. As a black hole pulls in gas from a companion star or a surrounding disk, it doesn't just gain mass, it also gains the angular momentum of that infalling material. Think of it as pushing on a merry-go-round. If you push in the direction it's already spinning, you'll make it go faster. But if you push against the spin, you'll slow it down. The final spin of the black hole is a delicate balance between these two effects. If the black hole consistently feeds from a well-ordered, co-rotating accretion disk, where the material is swirling in the same direction as the black hole's spin, it will be spun up, potentially to near the maximum theoretical limit. However, if the incoming gas is chaotic, arriving from random directions, the pushes and pulls will average out, often resulting in a more modest, slower spin. There's even a natural balancing point, often called the equilibrium spin, where the spin up from co-rotating accretion is perfectly countered by the spin-down effect of a specific type of radiation from the disk, leaving the black hole spinning at about 94% of its maximum possible rate. Many of the black holes we observe in X-ray binaries seem to cluster around this value, suggesting they have undergone significant accretion from a stable disk. But there is another, far more violent way for a black hole to change its spin, through mergers. When two black holes spiral together and collide, the resulting spin of the new, larger black hole is determined by the complex interplay of the original spins and the orbital angular momentum of the pair. It's a gravitational vector sum of colossal proportions. If the two black holes are spinning in the same direction as their orbit, the final black hole will be a rapid rotator. However, if their spins are misaligned or even pointed opposite to the orbital motion, the result can be a black hole with very little net spin. The data from gravitational wave observatories like LIGO and Virgo is now allowing us to hear these stories unfold. By analyzing the gravitational wave signal, scientists can estimate the spins of the merging black holes. Some events show clear signs of large, aligned spins, while others suggest more random orientations, hinting at different formation histories, perhaps a quiet life as an isolated binary versus a chaotic upbringing in a dense star cluster where partners were swapped in a gravitational dance. Measuring this elusive property, however, is one of the great challenges of modern astrophysics. We have two primary tools, each peering at the black hole in a different way. The first is through X-ray astronomy. As matter spirals inward in the accretion disk, it heats up and emits high-energy X-rays. Close to the black hole at the innermost stable circular orbit, the severe warping of spacetime means that this orbit's size is directly determined by the black hole's spin. A rapidly spinning black hole drags spacetime around so forcefully that this innermost orbit is much closer to the event horizon than it is for a non-spinning black hole. By studying the X-ray spectrum, and specifically a feature called the broad iron K-alpha line, that becomes smeared and distorted by the extreme Doppler shifts and gravitational effects near the black hole, astronomers can map the inner edge of the accretion disk. Pinpointing this edge allows them to estimate the black hole's spin with remarkable precision. It's like measuring the size of the drain in a cosmic whirlpool to determine how fast the water is swirling. The second, more direct tool comes from gravitational waves. The ripples in spacetime from a black hole merger carry an incredibly detailed fingerprint of the system. The pattern of the waves during the final inspiral and the ringdown phase after the merger is exquisitely sensitive to the mass and spin of the final object. By matching the observed signal to theoretical templates, scientists can extract the spin of the remnant black hole. This method doesn't rely on light or an accretion disk, it probes the gravity of the black hole itself. The fact that these two very different techniques, one using light from hot gas and the other using the vibrations of space-time, are yielding consistent measurements for spin, gives us great confidence that we are finally beginning to understand the dynamic nature of these cosmic gyroscopes. The mystery of their spin is not just about a number, it's a record of their life story from a star's final moment to the last chaotic instance before a titanic collision. Yet for all the theoretical speculation about what lies beyond the event horizon, a monumental breakthrough in 2019 gave humanity its first direct glimpse of a black hole's gravitational abyss. The Event Horizon Telescope collaboration unveiled an image that instantly became an icon, a fiery orange ring encircling a central region of profound darkness, the supermassive black hole at the heart of the galaxy Messier 87. This was not a photograph in the conventional sense, but a computational masterpiece assembled from data gathered by a virtual Earth-sized telescope. And at its heart lies our 28th mystery, the profound nature of the black hole's shadow and the elusive photon rings that could hold the key to testing physics at its most extreme limits. That central dark patch is the black hole's shadow, and it is a ghostly silhouette cast against the backdrop of its own glowing accretion disk. It is crucial to understand that this is not the event horizon itself. The event horizon is smaller, hidden within the darkness. The shadow is larger, a region of absence created by the black hole's unimaginable gravity. Photons, particles of light that pass too close to the event horizon, do not simply get pulled in. Instead, they are bent into wildly curved paths by the warped spacetime. The shadow's sharp boundary marks the point of no return for these light rays. It is the edge of the photon sphere, a theoretical region where gravity is so strong that photons can be forced into unstable circular orbits around the black hole. Any light ray that crosses this critical threshold is captured, either spiraling inward forever or being flung out to infinity. The shadow is therefore a perfect negative image of the black hole's gravitational grip, a direct manifestation of Einstein's general relativity predicted over a century ago. Its size and shape are a direct test of the theory. A perfect circle would confirm the Kerr metric for a spinning black hole, while a distorted, asymmetrical shadow would reveal the black hole's spin and viewing angle. The fact that the Messier 87 shadow is remarkably circular was a stunning confirmation that Einstein's theory holds firm even at the edge of this cosmic monster. But the shadow is only the beginning of the story. If you could zoom in with infinite resolution, you would see that the bright ring of light is not a single, simple loop. It is composed of a series of infinitely nested, razor-thin sub-rings, like the ripples from a stone dropped in a pond, each one trapped closer and closer to the edge of darkness. These are the photon rings, and they represent one of the most exciting frontiers in observational physics. Each ring corresponds to photons that have completed a specific number of orbits around the black hole before escaping to reach our telescopes. The first ring is made of light that skimmed the photon sphere, making just 1/2 orbit. The second ring is composed of photons that completed 1.5 orbits, the third 2.5 orbits, and so on. With each additional orbit, the photons are forced to travel a path that hugs ever closer to the event horizon, probing regions of ever more extreme gravity. The existence of these rings is a dramatic prediction of general relativity, but their detailed structure could be the key to discovering physics beyond Einstein. Each successive photon ring is exponentially thinner and fainter than the last, but also carries exponentially more precise information about the black hole's properties. Analyzing the first ring gives us a good measurement of the black hole's mass and size, but the second ring would allow us to measure its spin and charge with phenomenal accuracy. The third ring and beyond would begin to test the very foundations of the theory, probing for minuscule deviations from the predictions of general relativity that could signal the influence of quantum gravity. It would be like moving from a standard photograph to an image taken with a microscope capable of seeing the very fabric of spacetime. Any fuzziness or granularity in the fabric of space at the quantum level, any departure from the smooth geometry Einstein described, would leave a subtle imprint on the precise shape and sharpness of these higher-order rings. Capturing these photon rings is the next grand challenge for the Event Horizon Telescope and its successors. The current image is a monumental achievement, but it essentially blends the first photon ring with the light from the turbulent accretion flow. To isolate the second and third rings requires even greater resolution, an ambition that pushes the boundaries of technology. Plans are already underway to expand the EHT by adding new telescopes across the globe, and even by placing radio telescopes in space to create a baseline larger than the Earth itself. This would give us the sharpness needed to peer into this nested series of light and shadow. The photon rings are more than just a celestial curiosity, they are a cosmic laboratory. By studying them, we are not just looking at a black hole, we are conducting a precision experiment in strong field gravity, one that could ultimately reveal whether Einstein's sublime theory is the final word, or merely the prelude to a deeper quantum understanding of the universe. They are a ladder descending into the heart of darkness, each rung offering a clearer view of the laws that govern reality itself. But if the photon rings offer a way to test gravity with light, there is an even more radical theoretical framework that attempts to rewrite the very nature of reality to solve the black hole's deepest paradoxes. This brings us to our 29th mystery, a journey into the domain of vibrating strings and hidden dimensions. String theory, the leading candidate for a theory of everything, proposes that the fundamental constituents of the universe are not point-like particles but unimaginably tiny, one-dimensional loops of energy vibrating at specific frequencies. In this view, every particle we know, electrons, quarks, photons, is just a different note on a microscopic cosmic string. To make this elegant mathematical symphony work, however, the theory requires something extraordinary, that our universe has more than the 3 spatial dimensions we experience. It might have 10 or even 26 dimensions, with all but the familiar 3 being curled up into a space too small for us to perceive. Black holes, as the ultimate probes of quantum gravity, become the critical testing ground for these mind-bending ideas, offering a potential path to resolve the very problems that plague our current understanding. The most direct assault string theory launches on the black hole paradox is against the singularity itself. The concept of a point of infinite density is an anathema to a theory built on finite, vibrating strings. String theory's proposed solution is to replace the terrifying singularity with a vast, complex, and fuzzy object known as a fuzzball. Imagine the black hole's interior not as an empty space funneling down to a point, but as a gigantic, tangled ball of strings. This fuzzball would have a finite size extending all the way to where we expect the event horizon to be. There would be no sharp horizon, no vacuum, and definitely no singularity. Instead, the entire region is filled with this vibrating, stringy material. The key advantage of this picture is that it naturally solves the information paradox. Since there is no special boundary where information is lost, the information about everything that fell into the black hole is preserved within the complex quantum state of the fuzzball strings. When the black hole evaporates via Hawking radiation, that radiation is emitted from the surface of the fuzzball and carries away the encoded information in a perfectly unitary, information-preserving process. The black hole is no longer a paradox, it's just a very exotic, very dense star made of strings. A related and historically pivotal idea from string theory involves D-branes. These are multidimensional surfaces upon which strings can end. In the mid-1990s, physicists found they could describe certain types of black holes in string theory as collections of these D-branes. By counting the number of ways the strings attached to these branes could be arranged, they were able to precisely calculate the black hole's entropy, matching the famous result derived from the area of the event horizon. This was a monumental achievement, the first microscopic derivation of a black hole's thermodynamic properties from a fundamental theory. It provided strong evidence that string theory was on the right track, suggesting that a black hole's information content is indeed stored on a surface, aligning beautifully with the holographic principle. In this D-brain picture, the black hole is again a composite object without a true singularity, and information is saved. These theoretical triumphs are beautiful, but they lead to a crucial, testable question. If there are extra dimensions, could they change the very nature of black holes in ways we might observe? The answer is a resounding yes. In our familiar three-dimensional space, the strength of gravity follows the inverse square law. But if there are extra, compact dimensions, gravity could leak into them at very small scales. This would make gravity stronger than expected at extremely short distances. For black holes, this has a dramatic consequence. In a higher dimensional universe, it becomes much easier to create a black hole because the gravitational force required to collapse matter is achieved at a much lower mass. This opens up the breathtaking possibility of creating microscopic black holes here on Earth. The Large Hadron Collider, by smashing protons together at nearly the speed of light, concentrates an immense amount of energy into a tiny volume. If extra dimensions exist, these collisions could, in theory, produce a microscopic black hole. It would be an incredibly fleeting object, evaporating instantaneously via Hawking radiation in a burst of particles, but that distinctive burst would be a clear signature in the detectors. While no such event has been observed yet, setting limits on their production helps constrain the possible size and number of these hidden dimensions. Beyond particle colliders, the cosmos itself provides a laboratory. Gravitational wave astronomy offers another pathway to hunt for signs of these exotic objects. A higher dimensional black hole would not have the same properties as one confined to three spatial dimensions. Its gravitational wave signal, the chirp produced when two black holes merge, would be subtly different. The way the waves ring down after the collision would carry an imprint of the black hole's tidal love numbers, which are sensitive to the number of spatial dimensions. A deviation from the predictions of standard four-dimensional general relativity in the gravitational wave data from an event like those seen by LIGO and Virgo could be a smoking gun for extra dimensions. Furthermore, if extra dimensions exist, they could allow for a whole new family of black hole-like objects, such as black strings or black rings, with bizarre and unique gravitational wave signatures. The hunt is on to sift through the growing catalogue of cosmic collisions, searching for any anomaly that cannot be explained by Einstein's theory in a simple four-dimensional spacetime. String theory's approach to black holes represents the most ambitious attempt to heal the rift between gravity and quantum mechanics. By banishing the singularity and providing a microscopic account of entropy, it offers a compelling, if mathematically complex, vision of a consistent quantum black hole. The fuzzball and D-brain pictures transform the black hole from a destructive abyss into a complex quantum system, demystifying its paradoxes. Yet, the theory's greatest challenge remains its experimental verification. The predictions for extra dimensions and microscopic black holes are bold and specific, placing the fate of the theory squarely in the hands of observatories and colliders. Whether the evidence emerges from the precise analysis of photon rings, an anomalous gravitational wave signal, or a spectacular particle burst at the LHC, the black hole continues to serve as the ultimate arbiter, testing our most profound ideas about the fabric of reality. And so we arrive at the final, and perhaps most profound, mystery that binds all the others together. After this journey through 30 puzzles, from the paradox of information to the firewall, from the holographic principle to the nature of the singularity, we are left with a single, unifying challenge. Will black holes be the ultimate laboratory that finally unites Einstein's theory of gravity with the quantum world? Every strange property we've explored, every baffling observation, points to the same fundamental rift in our understanding of reality. General relativity gives us a majestic, large-scale picture of space and time as a smooth, curving geometric fabric. Quantum mechanics gives us an equally powerful, bizarrely accurate description of the probabilistic, particle-based world of the very small. Each theory is spectacularly successful in its own domain, but they are written in mutually incompatible languages. Where they meet at the edge of a black hole, the equations blow up into infinities and paradoxes. The black hole, by its very existence, forces this conflict into the open, demanding a new set of laws, a theory of quantum gravity. This is not an abstract academic exercise. The quest for quantum gravity is the search for the operating manual of the universe. Without it, we cannot truly understand the first moment of the Big Bang, the final fate of matter inside a black hole, or the fundamental nature of spacetime itself. Black holes are the perfect testing ground because they are the simplest objects in the universe, defined by just a handful of properties, yet they produce the most complex physical consequences. They are where gravity becomes so strong that its quantum nature can no longer be ignored. The information paradox is essentially a question about how quantum information behaves when gravity is ultra-strong. The firewall proposal is a desperate attempt to force quantum mechanics to work, even if it means setting fire to Einstein's smooth spacetime. The holographic principle suggests that the way to resolve the conflict is to radically rewrite our concept of reality, suggesting that gravity itself might not be a fundamental force, but an emergent phenomenon that arises from a deeper, quantum information-based system. What's thrilling is that for the first time in history, we are no longer purely in the realm of mathematical speculation. We are now gathering real, tangible data from these cosmic laboratories. The LIGO and Virgo gravitational wave observatories are not just listening to black hole collisions. They are conducting precision tests of general relativity in the most violent gravitational environments imaginable. Every chirp and ringdown is a data point. Does the signal match the predictions of Einstein's theory perfectly, or are there tiny deviations, perhaps an echo or an unexpected frequency, that hint at new physics? The Event Horizon Telescope, by imaging the shadow of a black hole, is directly probing the geometry of spacetime just outside the event horizon. Future observations aiming to resolve the photon rings will push these tests to even greater precision, potentially revealing the fuzzy, quantum-grained structure of space itself. Even the search for primordial black holes and the signature of their evaporation is a hunt for evidence of quantum gravitational effects in the early universe. The convergence doesn't stop with giant telescopes. Remarkably, physicists are now creating analog black holes in laboratories on Earth. Using ultra-cold atoms, lasers, and even flowing water, they can simulate an event horizon and study the analog of Hawking radiation. While these are not real black holes, they are quantum systems that obey the same mathematical relationships. By watching how information scrambles in these controlled settings, scientists can test ideas about fast scrambling and the emergence of spacetime from entanglement. A discovery in a tabletop experiment could provide a crucial clue that helps interpret the data coming from the cosmos. This multi-pronged attack, from the astronomical to the experimental to the purely theoretical, means that we are actively probing the edges of our knowledge. The path to a final theory is still shrouded in mystery. String theory, with its fuzzballs and extra dimensions, offers one compelling path. Loop quantum gravity, with its quantized spacetime, offers another. Perhaps the answer lies in a completely different direction we haven't yet imagined. But what is certain is that black holes will be the judge. Any proposed theory of quantum gravity must pass the black hole test. It must tell us what happens at the singularity. It must resolve the information paradox in a satisfactory way. It must explain the origin of black hole entropy. It must account for what we see with gravitational waves and the Event Horizon Telescope. The black hole is the universe's sternest examiner, and our theories are the students awaiting their final grade. The 30 mysteries we have explored are not separate puzzles. They are 30 different facets of the same brilliant, daunting diamond. Solving any one of them completely would likely mean we have found the key that unlocks them all, revealing a deeper, more unified, and undoubtedly stranger reality than we have ever known. From the silent, ghostly hum of a distant black hole to the fiery paradox of a potential firewall, from the mind-bending concept of a holographic universe to the terrifying simplicity of a singularity, this journey through 30 unsolved mysteries has taken us to the very edge of what we know and far beyond. We have stood at the precipice of event horizons, grappled with the fate of information, and dared to imagine gateways to other universes. We have witnessed the birth of supermassive giants in the cosmic dawn and listened to the gravitational echoes of their violent collisions. Each mystery, a profound question mark etched into the fabric of reality, reveals just how much we have yet to learn. Black holes are not merely exotic objects in space. They are the ultimate philosophical and physical crucibles, forcing us to confront the fundamental laws that govern existence itself. What makes this journey so exhilarating is the realization that we are not at an end, but at a magnificent beginning. The tools to solve these puzzles are now in our hands. The Event Horizon Telescope is no longer science fiction. It is taking pictures of shadows. Gravitational wave astronomy has opened an entirely new sense, allowing us to hear the universe's deepest vibrations. The James Webb Space Telescope peers back in time to witness the formation of the first black holes. In laboratories, we are creating analog event horizons to test the quantum nature of gravity. Each observation, each experiment, is a potential key that could unlock one of these 30 doors. Solving just one, truly understanding the information paradox, confirming the holographic principle, or witnessing the final state of an evaporating black hole, would send shockwaves through physics, irrevocably changing our understanding of space, time, and information. It would be a revolution on par with relativity or quantum mechanics, a paradigm shift gifted to us by the universe's darkest objects. The true power of these mysteries lies in their ability to ignite curiosity, not just in physicists but in all of us. They are a testament to the human spirit's relentless drive to look into the abyss and demand answers. So we turn this final thought over to you. After this incredible journey, which of these 30 mysteries captures your imagination the most? Does the possibility of wormholes as cosmic shortcuts fire your sense of adventure? Does the sheer paradox of information loss keep you up at night? Or is it the haunting idea that we might all be living within a holographic projection? The conversation does not end here, it's just beginning. Share your own theories and thoughts in the comments below. Let's continue to explore these ideas together. If you want to join us on the next adventure into the cosmos's greatest secrets, make sure to subscribe. The universe is stranger and more wonderful than we can imagine, and there are always more mysteries to uncover.